name's Stephen Redmond. I'm going to give you a little introduction to me and my career today, if you're interested. The talk today, and I'll go through an outline, is going to be about three things. I want to talk a bit about the physiology of touch, specifically as it relates to slip or incipient slip detection. I'm going to talk about tactile sensor design, particularly with slip in mind. I'm going to talk about slip detection algorithms, incipient slip detection algorithms. And it was a challenge to try to design a talk for 2.5 hours. And actually, I'm still not sure I'm going to go under if I talk too fast, in which case we'll go to lunch early. Or I'm going to run out of time because I feel like I have a lot to say about all the slides that I have, and I have about 100 slides, right? So you can do the math. So there's actually quite a high chance that we will push up against the time barrier. And the plan is that I've got 3 parts to the talk, so I'm going to try to give breaks. So we'll take like a 5 to 10 minute break after each part. That works, okay? So the title of the talk is Shining a Light on Touch Sensation. I'm not going to tell you why I named that. You will try to guess or figure it out as we go through. So who am I? I thought I'd leave this in. I actually removed these slides. I thought you don't care who I am, you just want to know the stuff. But then I thought, well, a lot of you are early in your career, so maybe you care about how people like me end up where we are, and I can tell you how I got there, and you can choose to avoid that path. So my background is in electronic engineering, and I had a big interest in signal processing, and then what would have been classical machine learning, which makes me feel old. Because when I was coming through neural networks were kind of a dying art, and sport vector machines were the winner at the time, and then everything turned on its head. So I did a Ph.D. in signal processing and machine learning. The focus was on telehealth in the home, and then I took an assistant lecturer position for a year at the university, so I was teaching signal processing, advanced signal processing. I went to work as a contract researcher for a startup company that then became quite a big company in Ireland called actually eventually became Redmond, Ireland, which is a multinational respirator company. And then I moved to Australia as a backpacker. So I thought, okay, I've been at this university for 9 years. Maybe it's time for a change. So I packed my bag and I went to Sydney. And by the time I came down the east coast of Australia to Sydney, I had spent all of them. I had 3,000 euros, I think it was at the time, and it was gone. And I thought, oh shit, I gotta get a job. And I realised I don't know, maybe it's something about my personality. I felt I'm not suited to service work, restaurant work, bar work. And so I called up a guy who I'd been in contact with not long. Cold called him and said, "You probably don't remember me, I sent you an email 6 months ago. I'm in Sydney, I'm about 100 yards away from the university, I'm looking for a job." And he said, "You know what, I'm looking for somebody, why don't you come in and have a talk?" And that was the start of a friendship and a collaboration that lasted for 11 years. So I went in as a postdoc, and I left as an associate professor in 2018. I came back to Ireland, mainly to bring my family home. We had 2 children in Australia, and then we felt like we were quite far from grandparents, and so we came back. I took a position at University College Dublin, and then sort of been dabbling in entrepreneurship. So I'll tell you a little bit about a company that we co-founded. It's an Australian company. It was founded by a previous postdoc and student of mine there, from Tactile, and then I'll also not talk too much about a foray into industry where I joined a large scale company called Fire One that just raised 125 million to bring an implantable heart monitoring device to market in the US. So that was a good experience. It was very interesting, but not my cup of tea ultimately. So, let's move on. So, what do I do? I would say my experience has been diverse. So, because I started with some basic skills, electronics and signal processing, I ended up being dragged to every meeting by my PI at the university. I met all these collaborators and got involved in all these different types of projects. So, particularly telehealth and human movement monitoring. And then along the way, and I'll tell you the story as we go through, I met a colleague, Dresden, who is a physiologist who's interested in human touch, and then we started a collaboration that just over time grew into all of the work that I'll show you in the slides today. So that was tactile neuroscience, big interest in electronic designs and instrumentations on building circuit boards with interesting arrangements of transducers, and inside there was tactile sensor hardware, which I'll talk about today. And then more recently, probably getting out of my depth, was I like to try to learn new things, getting into touch processing, so slip detection algorithms, grip force control algorithms, and then beyond, trying to marry that into the field of robotic learning, so deep reinforcement learning and imitation learning, which I won't talk about today. Okay, so let's get into the talk. As I mentioned, 3 parts, probably a little bit too ambitious in the time that we have, even though it's 2 hours. We'll do a bit on biology, which is a little bit, I feel, I could be getting out of my depth there. I was always the collaborator on these projects, so they were led by Ingvar's and other colleagues, and I was the engineer. I brought the expertise of analysis and contributed ideas to experimental design. But I'll talk about some of what we think we know about how humans feel friction and incipient slip. And then we'll move from there under the assumption that biomimicry is a good idea to be debated. I'll try to challenge you on that. We'll move into sensor design, and then the last part would be some applications, but very inward focus, really on what I've done, but there's a whole field there. I don't have time to review it. And we'll take a break after each part. So I'm going to start with a video that you've probably already seen, either this week. I don't know if somebody should maybe probably might have shown it, but this is a famous video.
Greg showed it.
It's already been seen?
Greg showed it.
Greg showed it, okay. So you can see it again.
It's good.
It's a teaching, right? So you got reinforcement is key. The more exposure you get, the more likely to remember it. So it's a great demonstration in my mind, because what we're showing is like a really clear idea that mechanoreceptors are important. So we have that she would pick up the match and strike it, and it all happens in less than a few seconds. And then they anesthetize the finger and thumb. It looks like at the nerve level, and then she will try to repeat the task, and you see the difficulty that she has. Now, at the risk of derailing my talk already, we were chatting yesterday, the day before yesterday, about this, and whether touch is really, because the reason to show this is to try to impress upon you the importance of touch for our dexterity. But is this needed for robots? Maybe vision is enough. Maybe she hasn't had enough time to practice. Maybe if she does this for a week, she'll do better. I don't know. But I'm moving forward on the premise that she could certainly do it more easily with the sensor touch. But given time to learn, maybe she could. I don't know. I don't think we know. So, mechanoreceptors or sensor touches seems to be important for dexterity. And I thought, since I was meant to be teaching here, I would go and look at some of these really famous papers by Owen Jones and Westing here from the 1980s. So this goes back a long way. And then there was, I'm going to give you a sort of history of this. There's going to be a long gap of about 25 years where not much in this area seems to happen, and then you pick up the match again. So this first paper in 1984, it's a task, and I guess I should explain it. The task is to lift a weight, which can be changed, using 2 surfaces whereby the friction can be changed by changing the material. So the material can be silk or suede or sandpaper. So they have different frictions, each one about twice as much as the one before. And what we're trying to see is that if they don't expect the change in weight or the change in friction, will the grip force adapt, and how will that happen? And the answer is yes. So as soon as we make contact with the object, we are adjusting our grip force and we can lift the object. And what we're trying to show here is that the grip force that's applied is scaled by the weight of the object. As you expect, you need enough you need to generate enough friction to lift the object. So we expect to see a relationship with the weight of the object changing. But also, for each of these, say sandpaper, there's a dashed line here, which is showing what's called a slip force. So if you were not to apply that much force, the object should slip. And there's a small safety margin above it, about 20% roughly above that we to hold onto the object. So it seems that we are getting some information on contact or when lifting the object that tells us what the friction of the surface is. Now I'm going to throw a confounder in here, which I feel was not well discussed or covered in these papers, is that the objects have different texture. There's silk, suede, and sandpaper. So there is a risk that we're learning from the texture what the friction should be based on repeated trials. So, and I felt that that wasn't well covered in these papers. So just bear that in mind as we go through. So this is where the first paper they wrote on this. They also do anesthesia, so they're anesthetizing the digital nerves of the proximal phalanges. The proximal is nearer to the body, so down here at this phalanx in the finger, they're putting a nerve block in to anesthetize the whole finger and thumb, similar to what you saw in the video, and then they're trying to lift the object. And what they notice is that when they do that, the adjustment to friction disappears. We don't adjust well to friction anymore, but we still respond to weight. So it seems that the sense of the weight of the object is not only coming through the mechanoreceptors, the cutaneous mechanoreceptors, it's coming from other parts of the hand, so maybe muscles. Okay, so then it develops. They make the setup more sophisticated. So they repeat the experiment. The setup changes a little bit. They add a few extra transducers, so they still have a ranger to know the height of the object. There's now an accelerometer that's been attached, so they try to use that to detect slip events and movement. But everything else is more or less the same. Looks a little bit different. And what we're trying to look at here is particularly what's happening around the timing of the grip force control. In the previous experiment just says, okay, they use enough grip force. But when the static grip force adjusts, is it after we've started to lift the object, when it starts to lift off the table, or is it before? And the answer is, it seems to be, and this has been shown in a few studies, it's happening before the object is even loaded. Not even before it lifts off the table. You'll have to apply enough lift force and load force to overcome gravity. But even before you start to pull up and lift the object, already you're scaling your grip force to the friction. So what's going on here? That's the puzzle. So we see these sort of behaviors. Let me explain what's happening. You have the grip force on this axis. You have the time running from left to right. We have the load force here. So this dashed line is meant to represent the time when we start to apply an upward force to the object. But already before that, by a very small amount, but already before that, the grip forces are separating based on the friction or texture, if you're being cynical. So what's happening? Why is it that we're feeling the difference in friction before the object starts to get an upward force, a sliding force applied to it? So, some takeaways from this. We are adjusting our grip force to friction. That small interval there is about 100 milliseconds. So it's pretty quick. We make contact with the object, we start to apply grip force, and then we start to lift. After that first contact, within about 100 milliseconds, we're already picking a different grip force to apply. They also do things in the experiment where slips are induced later, after the object's held in the air, and we see some interesting behaviours where the response to subsequent slip is within, again, about 60 to 80 milliseconds, and that's including 10 milliseconds for the force to come through the muscle. The muscle has to respond. It's a very quick response. It's believed that it's supraspinal, so it's going up to the brain and back down. So a very short latency. They do again with anesthesia and realise that in that initial grip for silk, in particular, the wrong grip force is selected and the object will slip. And with some, before I talked about at the beginning, with some repetition, eventually the participants will pick the right grip force to pick up the object. But trial and error is required because vision is not enough there. It's from a trial and error and try to just search for the grip force rather than calculate what's needed from the mechanoreceptor responses. And an interesting experiment done here, which is clever, which is they do two types of anesthesia. They do the digital nerves, which takes out the whole finger, but they also do intradermal, so they're just injecting, as far as I'm aware, anesthesia just into the skin at the mechanoreceptors to try to make a separation between just the cutaneous mechanoreceptors in the finger pad versus all of the other stuff that you can feel with the mechanoreceptors on the other part of your skin and in the joints and so on, muscles. And they show that the effect is the same. So they implicate here the mechanoreceptors. Once you take out the mechanoreceptors in the finger pad, this effect, this ability to do this goes away. So we're narrowing in on mechanoreceptors on the finger pad and something going on before we start to apply an upward force on the output. There's two more papers to come, but we need to take a detour because we're starting to talk about our mechanoreceptors, and the presenters have been discussing this slide because I think we all promised that we would include it rather than one of us do it, that you would see it at least 3 times. So this is a drawing I've taken from the internet of the 4 low threshold mechanoreceptors in the cutaneous skin. They are categorized in you can imagine in a matrix. One is to do with one dimension being spatial, which really refers to their depth in the skin. So if they're shallow in the skin, they tend to have a small receptive field. They're quite close to the surface and they can't really feel what's happening far away. So they have a small receptive field. So the 2 type 1 mechanoreceptors in the skin will have a relatively small receptive field. And conversely, the deeper mechanoreceptors, which are deep down the tissue of the dermis, they will have a larger receptive field. It's just mechanics, because if you're down here and you feel you couldn't really tell where the force is coming from above, it all transfers down. The different categorization between fast and slow is to do with the speed and adaptiveness of the response. So fast adapting, they tend to behave like if you think in this way with a high pass filter, they respond to change, dynamic change, but then go very quiet. So if you change, a sudden change, and maybe apply a force and then hold the force static, they will burst fire and then just go quiet again. So that would be the FA1, the Meissners, and the tuning corpuscles, which are exquisitely sensitive. They don't feel a vibration even up somewhere else on the arm that probably fire in the fingers. They're very, very sensitive. Ruffini organs taught to encode stretch, but also to respond to pressure, and are again deeper in the tissue. This is important as well to look at. You'll see this pattern appear in some of the sensor design later. These papillae between the dermis and the epidermis. It's not just a fascia that's between those 2 surfaces. They interleave with each other, kind of interwoven in these little papillae structures embedded in there, and it's a repetitive pattern that lines up with the fingerprint ridges. So you see this pattern that repeats one square fingerprint ridge, and the positioning is interesting as well. So down here you have Merkel. This is SA1. So these are really high pressure sensors, but will respond a little bit to vibration, and then much closer to a little bit closer to the surface of the skin, we have Meissners, which are the vibration sensors. So this is interesting because there's something in this structure that they're all positioned around this interesting structure that's, well, I'll show you later. It's that this, with the fingerprint ridges and the papillae structure, allows the skin to undergo shear deformation. It can stretch across its surface. If it was just flat and planar, that would be difficult. The skin would have to undergo some sort of tensile extension, so you don't need that. You can just unfold. So this seems to be important, this structure that allows the skin to deform sideways. Could play a role in slip protection. I had an argument, no, I had a discussion with somebody at a conference once about whether that's what our fingerprints are for. Other people will say our fingerprints are for taking excess water away, because if your skin is a little bit moist, the friction goes up, but if it gets too wet, it can become slippery, so we try to optimize our friction or our hydration level in our skin for friction. So that can be true. The 2 things can be true at once. I mean, we could have evolved these patterns to serve multiple purposes. One being maybe slip detection, one being texture recognition, that they're little bumps, so when you slide them over the surface, they'll bump up and down and catch and let go. Hydration optimization could be another reason. And the other reason that the person was saying this is the sole reason for fingerprints is to stop delamination. It stops us from getting blisters. If you had a flat surface on your skin, you do a lot of work with your hands, and you get blisters. So this flexibility allows the skin not to blister, and that's probably also probably true. So I don't take the view that, I don't believe in design here. It's evolution, and if that's the property that allows us to have multiple benefits, then I think that's possible. Okay. And there's lots of other stuff in the skin, and people are really into this. C fibers and afferent effective touch, and there's thermal receptors and nociceptors, pains, sensors, and so on. So there's a lot more going on than what I'm on here. So how do we know about these receptors? Well, there's some great papers from back in the 80s, Valvo and Johnson, where they developed this method of microneurography, where they stick a needle into the nerve, and the needle is huge compared to the size of the nerve, and the axons, with this bundle of axons are going up. The needle is enormous, gigantic. And yet somehow, by poking around very carefully and bringing the needle close to the afferent, they can get close enough to record what's called single unit response. So every afferent, a nerve might innervate not just one mechanoreceptor, but several mechanoreceptors. So it might be like one nerve innervates maybe 5 or 6 mechanoreceptors in the skin, and that's called a unit, an afferent unit. So you can get close to a unit, and you do it by sound. So people also use ultrasound guided now, so they used to get close to the nerve, they use ultrasound to see where they are, but then they listen and they try to figure out how close to an afferent. And then don't move, because if you move, you think about it, it's big needle, tiny, but still big relative to the nerve. We're trying to keep the recording stable for several hours. It's very difficult. So this is what it looks like, and then if you can hear.
I'm trying to understand what happens.
So this is Vaughan Macefield, and then have a Camus in the background. It's a hissing sound. Is the afferent firing?
It's an SA1.
What is SA for?
Slowly vacuuming, so it keeps on firing as I'm maintaining the contact.
So what's happening there is they've just found an afferent, they think that the needle is stable, and they're characterizing, trying to make a decision, is it SA or FA, is it one type 1 or type 2? So they use a long frayed hair and they poke around the skin, and once they think it's isolated, then they'll map the receptor field and just figure out roughly how big it is and make a decision. And then we start the protocol. So you'll see some video later of the robot pushing on the finger to stimulate, to generate the force that will elicit the response. Okay, so we now know a little bit more about mechanoreceptors. We can go back and talk about the next 2 papers from this 1987. These 2 papers appear back to back in the journal, so they're really part of the same experiment in a way. So the apparatus is more or less the same. What's different now is that we have it's a vacuum. It's like a little bag with sand in it, and you suck the air out of it, and it clamps the forearm. So the hand can't move, because if you've got the electrode in the median nerve up here in the upper arm, any movement might move it away from the afferent. So you've got to keep everything very still. And then the experiment will be done by flexion of the wrist, so they'll lift the object just using the wrist like this. And it's the same idea, you just lift the object, the friction will change, and we'll look at this time the afferent responses. Now we're getting closer to what's happening at the contact, because there's something funny going on at that initial contact of lifting. We're trying to figure out what it is and which mechanoreceptors are responsible. So there's a lot of information here, so don't worry about that. I'm just going to point out some interesting parts, and if you're interested, you can go and dig out the paper later and have a look. So let's have a look at the 4 different mechanoreceptor types. Over here we have an FA1, so these are our little shallow vibration sensors. We have, I think it's, there are four afferents, 2 from 2 different people. It doesn't matter, it's 4 different mechanoreceptors. And this is just sort of n equals 1 for each of them for a lift. And what we see is there's a lot of firing that happens before the loading phase. So before the object even starts to get lifted, when that initial contact is made, they start to fire. But it's been messy, there's a lot going on. But remember, we have a lot of mechanoreceptors, and the finger pattern is 2,000, and they're in different proportions. So there's a lot of mechanoreceptors there, so you can have some variability, and the brain will makes sense. Essays, bit messy, but again, there's a lot of activity happening before. So on that contact could be just from the normal force, but it could be from something else as well. What about, here we have FA2s. So these are our deep in the skin, really sensitive vibration sensors. They have a tendency to respond aggressively to sudden events. So when you move, when you make first contact with the object, you're lifting the object but it stops moving. So these are the kind of events. So here's the, you look at the load force, this vibration happens at the top of the load force. After you lift the object and you stop lifting it, then they fire. And when you start trying to move back down, here's where it starts to move, and then they fire. So they tend to be responsive to contact events and sudden events, and they're very sensitive. They can pick up vibration on remote parts of the skin. So probably not important for slip detection and what we think we're trying to look pretty effective. And then SA2s they're a little bit paradoxical, and this has been shown in other studies as well, studies with torque, where they're quite capricious. They will sometimes be firing, and then you stimulate them, they'll stop firing. And then another SA2, which will be nearby for the same stimulus, will increase its firing rate. So what's going on? Well, it's probably just to do with how they're embedded in the skin, whether they're already under tension, and whether that tension is being released, and they have an orientation. And so it's a really complex picture. And so it's a bit simplistic just to expect them to increase their firing rate when there's some stimulus at all times. It depends on what's happening in the skin, the mechanics of the skin local to the mechanoreceptor itself. And so how is that useful if it's so unpredictable? Well, the brain, I assume, can make sense of this information, right? We learn the pattern. So, and I'll show you another drawing in a while that sort of reinforces this, the idea that sometimes they fire more, sometimes they fire less. Depends. So, that was an interesting experiment. And then the last of the four papers, it's a quote. Since we did not adequately measure the precise skin deformations influencing the units, the present results were principally based on qualitative assessments. So what they're trying to say is that there's something going on with the skin, and we can't see it. So it's hard to know exactly why the mechanoreceptors are responding the way that they are, because we're not looking at the skin. So it's kind of opening an avenue for further research. Right? Let's start looking at the skin, which is why I put this. Now, this is the last of the four papers from Johnson that I want to talk about. This one, as I mentioned, is going to work immediately after this previous paper in the journal, and is really part of the same experiment. And what they're doing here is to really try to focus in not just on the lifting, but try to get in close to the slip issue, like something going on with the slip on first contact. And they even go as far as inventing a new apparatus, which is used in the paper, which is a handheld thing. The challenge is that they can't see the skin and they can't control where the mechanoreceptor is located. So the idea is you're literally poking around in this bundle of thousands of afferents, and you just get lucky whichever afferent you get. And then you go searching for it. It could be on the hand, it could be on the thumb, and you don't want it there, so you go look, hoping that it's on the pads of the fingers that you want to measure from. And it might not be in the place where you care about, maybe it's around on the sides. So you have a lack of control there, which makes an already difficult experiment even more difficult. Because you search for this afferent and then you find one and you're really excited, and then you go and find out where it is on the skin, and it's in the wrong place as far as you're concerned. And so with this apparatus, they can just get an afferent and then go and poke it. No matter where it is, just give it a look with this device. And this graph here is the paper is packed with data, and it's all quite qualitative, and it's as impressive as it is, it's a little bit chaotic because they're trying to get a handle on a very complex issue to do with the interaction between slip and skin and mechanoreceptor firing, and so it's all very qualitative. So this one part of it is that this is from this device here where they're sliding. They have this effect where they rub the probe along the skin, and the lateral force, the tangential force grows, and then eventually they have an accelerometer that they can see what they think is, I would call it gross slip, very overt slip, the accelerometer judders, and they see a drop in the load flow. So we know there's been a big slip event that's happened here, a little earthquake that's happened. But in the run-up to that, the FA afferent is firing, the skin might be stretching, but there seems to be something going on, and the implication is that there's some incipient slip, some small localized slip that's happening, and that's why the afferent is firing. And here's another example of that here. So this is the inverted slip at this point, but there's quite a lot of activity in the run-up to that. So they're kind of coming meandering closer to improve, but they never quite get there. I have any question on them. So that was 1987. At present, we can barely speculate on possible mechanisms underlying the influence of the surface material on initial response in some of the FA units. Perhaps small frictional slips or sliding motions occur at very low grid forces which are caused by forces which always exist on the plane of the contact surface, and the frequency of such slips we expect should be higher, more slippery material. So they're speculating on what's probably going on. There must be some skin slip happening near those afferents that we can't see it. Now, there's a paper in 2009 by Jones and Flanagan, which is a nice review paper. So if you're looking to go into this area, it's a little bit old now, so it's probably, what's that, we're back 16 years. So it's a little bit old, but it does capture all of that stuff that they did in the 80s and summarize it really nicely. And this is their sort of cartoon diagram of it. So what we're saying is we have this reach for the object, make contact, and then there's this preload phase where we sort of establish the contact and then we start to lift. So just before the load force rises, there's this sort of preload phase where interesting things happen. There's a bunch of firing on the FA and SAs. We don't think the SA2s are doing anything, and we can't quite figure out, sometimes they fire and sometimes they don't. And the FA2s, we don't think they're implicated because they just respond on large events like contacts and stuff. So the spotlight's turning towards the FA1s and SA1s for the most part. But don't close your mind to the others, right? They could still be anyway, so I'm trying to teach you stuff, so when you go and have a read of that paper. Now, the segue into this is that in around that time, 2008, 2009, I was working as a postdoc in UNSW, and as I mentioned, I was being dragged to every meeting that my PI had a collaborator with, and sometimes you get into projects. And one such project was a really large government-funded project called Thinking Systems. It was enormous, multi-university, hundreds of people involved, and one branch or one pillar of that was a focus on the human hand. And there I met Ingvar Brznex, who was a neuroscientist working at a research centre nearby. And he was frustrated that he had all this data from various labs. He had data from microneuropathy data from monkeys recorded from humans recorded in Sweden, and he had monkey data recorded in Melbourne, and he didn't have anybody to help to analyze it. So I volunteered, and that was the start of a collaboration. So the first paper that we wrote was, that I wrote with him, co-wrote with him, was analysing this data from monkeys, and the problem was coming into contact with the monkey's finger would be twisted in some direction with some torque and then unloaded and taken away. And we were taking an ensemble approach. The idea of an ensemble is that because we can only record one mechanoreceptor at a time, and we want to decode what that information is there, we realize the brain is actually taking all the mechanoreceptor information and decoding it. So how is that even possible? So we would do the same protocol and record many recordings from different afferents. So I think in this paper we're 83, which is still a small number relative to the thousands that are in the skin. But then you would make the assumptions, the ensemble assumption, that everything else was equal. It was as if we recorded all 83 in parallel simultaneously, which we didn't. Right? We just had a robot that would apply the same stimulus over and over again. But with that assumption, you can put those 83 afferents in parallel, and you can develop signal processing or machine learning methods. In this case, it was a classification approach. We're just showing that we into these discrete levels of torque direction and torque magnitude and so on, and normal force level, that it is possible to classify as a normal or as time runs on of those different forces, and to see which afferents are more implicated and contain more information. So we see things like for normal force magnitude classification, SA1s, the pressure like sensors, they contain information. Anyway, the point was that this was the first time we met, and we came up with an idea that was we could use ensemble methods to try to show this information is embedded in these data, even if it's difficult to see it in the single unit recordings like you saw in the Johansen papers, which are a little bit chaotic at times. So we went on then, and instead of just doing classification, we then tried to do regression to show that yes, it is possible to get a continuous value out of these mechanoreceptors. So this was work that we started to do at Hella because we won funding to do some of this work. So the Journal of Physiology, that's 10 years ago now. But so where to from here? Well, it was around that time I think Brad asked me to go for coffee, and he said, I have to say I was a little bit disinterested at the time, not realising it was going to consume the next 15 years of my life or something. But it's a friction scene. It's all about friction. It's just what washed over me, like Ingrid has a new idea. Like it's, the sun has risen. Like every day there's a new idea, right? It's full of them. So he said friction is where it's at, and then he started talking about it. Roland Johansson did this work in the 1980s, and I talked to a colleague about it in Sweden, and he said, don't touch friction, it's too hard, you're going to ruin your career. That's good advice. And he just said, no one's done anything on this for 25 years, and why are people not looking at this? It's so important. And so we wrote a grant application to try to study this stuff. And the idea was to take the methods that we were using for the data we already had, ensemble methods, and we would just bring them over to the friction problem. So we would do similar experiments. We would get a robot, and the robot would simulate the finger, and we would control the friction and texture. We would take an ensemble of recordings, and we'd get as many mechanoreceptor responses as we could, and we'd put them through our methods that would show that the information's in there and how quickly we could possibly decode friction and so on. So this is the approach where trying to get around what a perceived limitation of the Johansson work, that we're 3D printing different textures, and then we're trying to modify the friction. And I'll talk a lot about this challenge actually, because I've got loads of challenges for you. So we would have a no treatment, so dry condition. We would have maybe put some oil on to reduce the friction, and then we have this sticky. It's called Ribbo, it's a trademark. The Australian cricketers use it. They put it on the cricket ball because it helps them when they want to put spin on the ball. They can get some friction between the hand and the balls to get the ball to spin. So it's kind of tacky substance that will increase the friction. And that's the idea. So it does work. So in this paper it's 14 afferents, which is not as high a number as in the other papers. And I guess the takeaway here, I know there's a graph here and lots of information, but the takeaway is that even though we had the robot moving with different speeds in different directions, we have three different textures and different frictions, it is possible to decode from this ensemble of recordings what the friction level is. And Heva was looking to win best paper at Eurohaptics in 2014 with this work. But I have to say, there was always something unsatisfying about it. One being the machine learning approach. Often you don't learn anything with machine learning. The machine learns, you don't learn, right? So you give it the data, it learns where the pattern is, and then you're none the wiser as to, it's a bit black box, right? It's running by and all that stuff. So we weren't really elucidating what was happening with the mechanoreceptors there, but we were showing that the information seems to be embedded. But the subtle difference here, which maybe we should have noticed a priori, is that the ensemble methods with the monkeys and the humans, where you get the robot to perform the same process over and over again, really the same thing more or less should be happening. The interaction between the probe and the skin and the mechanoreceptor should be fairly repeatable every time you would expect. But with slip experiments, it's demonstrably not, and I'll show you some videos of that happening, that it's more unpredictable. You cannot predict when the skin is going to slip. So the firing of the mechanoreceptor has this inherent variability tied to the slip, the occurrence of the slip event. So when you try to build an ensemble, then you're sort of putting more the data with much more variance on top of each other and then trying to decode it. So it's more challenging to do. I think we were struggling with that a little bit. And so really where I'm trying to bring is the whole first part of the talk is to try to bring you towards skin mechanics, because we realized at that point what we should probably be doing is we should be imaging the skin and doing the microneurography at the same time and trying to relate the skin events with the microneurography, the afferent firing events. And maybe that will be done in the ensemble, and we can tie the slip event to mechanoreceptor responses across an ensemble. So that was kind of a new ambition, a moving target that we were chasing. So this concept of incipient slip, or beyond spec as called localized slip, just relates to part of the skin slipping at any one time. And the reason that this happens, I've already alluded to this, is that your fingerprint ridges, capillary ridges, they can open and fold like an accordion. So they can fold up and become nice and compressed, or they can open out and become nice and stretched. And so that shear deformation can happen. And depends on which way you want to say it, but it is essential that that should happen if you want to have incipient slip. If the thing was completely rigid, you can't have incipient slip. The whole surface is either stuck or it's moving. So if you want to have part of the skin slip and the other part stay stuck, then there has to be movement between those two parts. But the skin is not going to tear and disconnect, right? So in order to have the continuity of the skin between the two parts, there's one stuck and one slipping, there needs to be some stretchiness between them. So you could be just stretch the skin, and it's, I think that would be difficult to do. The fingerprint ridges allow that to happen really naturally, so it's probably one reason why we have it. And a lot of animals have fingerprints, so if it's something you're interested in, you can look at animals that climb trees. Possums have little fingerprints like this, monkeys have, so like it seems to be, this is my anecdote, a loose correlation between fingerprints and dexterity, so maybe we do need them.
Stephen, can we ask questions?
Yeah, far away.
Do you think the direction of the fingerprints matters? Because intuitively you can stretch more this way and not like along ridges.
Yeah, I think so, yeah. And like, if you look at it, I mean, my fingerprints kind of go, they follow a whorl, which is kind of, they come up on this side and they go this flat way across the top and they come back down. I think that is probably important. And it's something that we should study if people are already studying about the way you would lift the object, maybe is a way to study that perhaps. Whether you take it like this, or you take it from the side, or upside down. But I think it is important. Yeah. But I don't know why, in what way. Yeah, do ask questions. Yeah. Challenge me as well. I say, like, I'm saying stuff to you, and you're like, oh, he said it, that's the way it is. Like, I'm probably wrong. So, maybe I'm misrepresenting what's in the paper, or maybe the paper was misrepresenting what was in the data, and so, like, you gotta be challenges. So, how is this imaging done? I'm saying to you that I think it's important that if we want to learn more about this behavior, this phenomenon, we should study the skin movement when experiencing slip. So what mechanism, what apparatus would you use to do this? So traditionally the method used is this, some people call this frustrated total return reflection. That's wrong, it's a misnomer. I'll talk about frustrated total return reflection in another slide. But this simply uses reflection and transmission coefficient. So if you have any knowledge of Fresnel laws, the idea, let me say it differently. When you're trying to pass energy from one medium to another, the amount of energy that will pass into the next medium depends on the matching of the impedances of those materials. So in an optical sense, it would be refractive index would be a measure of that. Impedance and speed kind of go together, so like speed of light changes in different materials. So when the refractive index changes, if it's a very small change, most of the power will go into the next material. If there's a big difference in refractive index, you get a lot of energy expected. It's a universal thing. It happens even in electrical systems. If you have an impedance of a transmitter and a load, if they're not matched, you get a lot of power reflected back. So it's universal. So how is that useful? Well, the fingerprint is undulating, so not all of the fingers pad is in contact with the object. So what we do is we have a piece of glass or whatever, it can be perspex, right? Something transparent, and the skin makes contact. Where the skin contacts the plate or the material tends to be the refractive indices are better matched. So you can get more of the power, the light to go through into the skin where it gets absorbed. So those bits will look dark on the image. So the bits in between, which would be the values of the fingerprint, there's air, maybe a bit of water in there, depends on how it's set up, there's probably air. The refractive index difference would be quite large. You're going from glass 1.3 to air 1, more or less 1. You get more power reflectives. These will look bright, and that's what you see when you so the fingerprint, the ridges look dark here because the skin is absorbing the light there, it's transmitting through it into the skin, and the bright parts are where the light's being reflected back. So it's a simple transmission reflection based on difference in refractive index on the hand side. Some clever tricks that you use in optics, they're not always necessary. You can use a half mirror if you want to have what's called coaxial. You shine the light up, half of the light will get not shown here, gets reflected away, the other half goes straight through. Then on the way back down, half of this light will come through to the light source, and then the other half of that will come over. So you end up with a quarter of the light making it to the detector, but it allows you to have everything coaxial. So it's as if the camera and the light are looking in the same direction, but they can't be in the same place at the same time, so you can move the camera over here with a half mirror. So some clever tricks like that, but it's not necessary. You can take a slightly oblique view of the light source here, as we've done in the past in the camera, and that's okay. You just don't get the maximum difference in refractive index or reflection transmission will happen normal rather than premium. So what can you do with this stuff? So I've got a couple of little detours in here. It's just some interesting stuff that's not necessarily core to the talk, but this is work. Sophie was a student in my group, and this is work done in collaboration. So like a lot of credit to Benoit Delhay and Philippe Belg in Belgium, because this is their rig. And this was done during COVID when everything went sideways, and we were building stuff, and we didn't get finished. And then we thought, okay, maybe collaboration is a way to be productive. So Sophie went to Belgium eventually and collected this data. But this was the first paper showing the behaviour of the skin slipping under torsion, which is often ignored. A lot of these experiments are just drag in one direction. But torsion is really important. I'll probably reinforce this later, in that it's very difficult to lift an object without having torsion on the finger. And we actually experienced this in some robotic experiments where we're trying to grip an object and we just want to have a normal force. And every time we would try to lift it, it would twist. And it's very frustrating because that would increase the likelihood of slip. We had to put markers on the table. I'll show you the experiment later. And we had to line it up so perfectly in order to remove the torque. And then I just thought, why are we doing this? Like, obviously we should be, we're so focused on linear forces. Torque is obviously a big deal. So that's kind of the next frontier, right? So this is what the skin looks like slipping. And you can probably see it, but if we do some processing on that, we end up with this is difference in rate of rotation. We know the rate of rotation of the plate, and the skin should go with the plate if it's stuck to it as it rotates, and as soon as they differ from each other by rate of rotation locally, you can say it's slipped. There's no reason why the skin is not moving and the plate keeps going, they're rotating at different rates, so you can see the skin slip. So we get again this incipient slip pattern, which tends to happen in the periphery first and propagates in towards the center, and it's stimulating probably all of the mechanical receptors on the way in to tell us that things are going wrong right, depending on what we're trying to achieve. It could also be this like mechanical, what would affect the mechanoreceptor. It's not rate of rotation, it's probably things like strain, stretch, and change in shape and elongation. So that's shear strain rate. Now, that one method that I showed you there is a number of different approaches. That would be this one, where we use a reflection coefficient to get the pattern. There are other ways to do it. So some people have used frustrated total internal reflection. The idea here is that you shine the light into the plate from the side, and it would ordinarily just pop out the other end. But it's kind of bouncing around in there. And it's below the critical angle, so if you know about total internal reflection, you shouldn't be able to get light to leave the material there. It's just going to get reflected. Like when you're in under the water in a swimming pool, you can see reflection. It's like that. It's not coming out. But it's the quantum mechanical effect. If you put a material beside it that has a higher refractive index, you can occasionally get some photons in the surface leave the material. You get a pattern like this. So that's one way to do it. I just showed you this way. And then some other methods to have the light coming obliquely. And actually, people are playing clever tricks now with so kind of go a bit deep here. But it can be a bit difficult to know in some of the imaging methods where the contact area ends. It's not so clear cut as this. Sometimes you can see the contact area, but you can also see the finger is fainting behind. And it's hard to know where the border is. And people are playing clever tricks where they're multiplexing light, they're shining light. They might shine light up here, and then they turn that off, and they shine this light, and they go back and forth, and they try to show where's the contact area. So there's some engineering tricks to try to get around that problem. So anyway, there's different ways to play with light and reflection. And also prisms can be used. So this is also like a frustrated total internal reflection effect, where the prism you normally just see an image, but you're actually looking at an image of a diffuse light source here. But then when the skin comes into contact, the light escapes and looks dark. This is a device we built in the lab, and unfortunately somebody didn't publish on it. So I've got to pass it to the next student to try to finish. But the idea here is to build an apparatus where we can do, I'm getting a bit ahead of the talk here, we can do active touch experiments where it's totally free to hold and change the direction of and so on, and we can image on both finger and thumb and measure all the forces. It's a work in progress. Let's speed up a little bit, I think. Other imaging variants. I love this one. This is really new. So from Benoit's lab, trying to get the whole finger in 3D. They've got multiple camera views around, and they're playing all sorts of games with light multiplexing to try to illuminate the finger. And then they're trying to track the skin deformation during slip. And in order to have some trackable features, they are sputtering paint onto the finger pad before they start the experiment. A lot of work. So I think you got a best paper at your lab last year. So yeah, it's great. And it's really challenging stuff. Big setup and yeah. And this is one of the challenges I'll talk about that they're trying to get around here, is that usually we only image the finger pad in contact with the glass, and we don't see anything else. As if there's no mechanoreceptors anywhere else except for the contact area. It's not true. We don't get to see the skin in those areas. So here we get to see the contact area and everything around. People are even using, this is from Hans Als, he's using optical coherence tomography, which is kind of like ultrasound using light kind of approach. You can see a couple of millimeters into the surface of the skin, so you can see things like here they have the dermis and the dermis below, and you can roughly make out the papillate structures there. And they're sliding across the bumps and watching the skin changes. So lots of methods. So I'm going to push on and then we'll take a break through this part. So some experiments. So work that what can you do with all this stuff? So this is the experiment set up in Ingvar's lab where we are bringing, using the robot, measuring the forces, using an optical method to bring a plate into contact with the finger. And it's not just any plate, it's a very special plate. It can control friction. So the way it does it is, you can just about see the plane here, there's some piezoelectric elements on the glass, and they vibrate ultrasonically, really high frequency, about 40 kilohertz. And that will change the friction of the plate, because it makes and breaks contact with the skin. So when it's not in contact, there's no natural force, the friction goes down, and that way you can control the friction. So I'm going to speed up a little bit because I'm not going to have time here. But the idea is that we will just make contact straight down and see is that when the skin is getting that information about friction. There's some slip happening, and you can come in at 20 degrees to the finger and then ask the participant. They get asked, was the first stimulus or the second stimulus higher or lower friction. You have to, it's a two alternative force choice. And this is what the friction plate looks like. High friction just means off. So here is the robot coming into contact with the skin. This is the image that we see as the contact area grows. You can see the fingerprints. Also a bit challenging because the image improves as the moisture kind of spreads across the plate. So there's always a difficulty right on contact to see the initial contact to see the image because the moisture hasn't really come up from the skin onto the plate. And here the plate is on, it's called low friction, but the plate's vibrating here. But there is something, throwing a little bit of shade on this stuff, there is something about this friction plate when it vibrates, is that you get these little pockets where it's not clear that the skin is ever in contact with the plate. So it doesn't seem like a natural phenomenon for a normal material to me. And also, you can feel if it's on at high power, it's warm. You're making or breaking these chemical bonds at the skin and the object. The skin can start to feel warm, which could be glue, so it's something to be careful of. Well, in summary, for this experiment, we can't tell the friction. If your robot brings the plate in, it doesn't matter if it's high or low. You ask them which was higher, lower friction. Come straight down the finger, you can't tell. Come in at 20 degrees, maybe get a bit of slip happening, not much happens. They can't tell. So, what's going on at the contact, or initial contact? Why is it that in the Johnson experiments we can feel friction on first contact, and when we bring the object into contact with the robot, we can't? So this is another paper, edition today, from Dr. Dresden with Ingars and Lawrence Wilmot. Slightly different approach. So instead of the finger being immobilized and the robot coming to bring the surface in contact, here they have it's active. Like you have to use your own muscle on a guided rail to bring the finger into contact. I'll play one more time quickly. To bring the finger into contact with the vibrating plate, and the friction will be changed. Same idea. It's a two alternative force choice, and so they bring it down themselves. And then there's an analysis. Where they process the images and look at the amount of skin deformation on that contact. And the argument is that the skin splays, it diverges on contact, which makes sense, physically it makes sense, and that's the method. Now the difference is in this experiment, which is very similar to the previous experiment except for it's more active, that in this experiment they can't tell the difference. So what's there's a yeah.
I'm just guessing.
Yeah, go guess.
I was thinking maybe a little bit of the side motion, or I think I heard Ingvar's give a talk about, like, fragmented talk about this a few years ago.
I think so, yeah. We had a little email discussion. I was waiting for my bus at Berlin airport and I was sending emails to him and he was replying, and I was suggesting that maybe, because in the paper they say, no, it's because in one paradigm it's passive, right? So because I'm going a bit deep on this, but it's believed that when you activate a motor functions, when the brain tries to do something, that it gates the sensory input, so it sort of ignores your sensory input. It says, hang on, we're busy doing something now, we're not listening to inputs anymore, okay? And that in an active protocol where you would move the finger, you're not using that sensory information anymore. It doesn't make sense to me that would be such a big difference. But sorry, I was trying to play the video just to show they have the finger with a 30-degree angle on the little rail apparatus. And when you see it from the side, I feel like mechanically that will be applying a sideways force to the finger. Sometimes at 30 degrees, so the finger is kind of comes under a force, but it can be put, it looks like it could want to move to the side. And I was reading through the supplementary material last night, and there is a graph where it shows some 0.2 millimeter lateral movement. I think I understand, I wasn't sure from that graph. So I think there's a little bit of sideways movement. So anyway, I hope I don't tip Ingvar's hand, but I know he's studying this idea of lateral movement versus divergence. So is it a divergence, a spreading effect, or is it the fact that we have this sideways movement of the skin? I think Yeah, it's probably longer. It is sliding sideways. So it's interesting, but like two very similar experiments, different but similar, that you end up with in one scenario they can feel the difference in friction, and another they can't. And I still think it's to do with skin deformation. So moving on. So anyway, they give some examples there, but I don't think reasoning why, but I don't think that it explains it. So Ingvar's did another experiment then. It's published recently where it's more like active touch, so they're actually doing something. The two setups are, I'm very lazy here, I just grabbed the graphical abstract, so it's quite full, but the two things you focus on is, in this scenario here, they call it reach and touch, so you have to just reach out and like touch a surface, the glass plate, and you're not allowed to prop yourself against anything like this. And in another scenario, you would sort of hold your hand steady like this, and then you would touch, so the hand is stabilized in some way. That's the only difference. So one is like the whole, you got to control the whole arm, or you can stabilize the hand and just bring the finger in. And the results are that if you are free to move the whole arm, you do very well at feeling friction. And if you stabilize the hand, just move the finger, you don't do as well. A little bit of chance, but not as well. And so it just seems to be a lateral movement issue. That when you're trying to reach out and control your whole arm, you don't have that kind of control, so the finger will slide around on the surface a little bit. Whereas when you stabilize the hand and just move it into contact, there's not that much opportunity for the skin to slide around. So you find it more difficult. So this sideways movement seems to be important. And that's just the protocol for that one. So it's quite subtle. I mean, here you see this what we call supported touch. So the hand is supported, shouldn't see a lot of movement. One friction, electronically changes another friction. So medium and high, and then this will be, you won't see any difference. This is free touch, so the arm is unsupported, comes in maybe a little bit wobbly, one friction, the next friction. So very subtle, and yet in one paradigm you can feel the difference in friction, and the other you can't. I want to get to the end of this section so we can take a break. Also, a very recent paper is, yeah.
So the idea was if I free move, I'm better at inferring whether I slip or not. Is that
If you free move, you don't have kinematic control to avoid slip. Some slip might be some hypothesis that your hand is a bit uncontrolled, and so this kind of movement happens on contact, and then the information is acquired at that time.
there might be another explanation there, right? Like when you have more actuators that are capable of measuring things, you have a much better resolution in terms of inferring force. This is just generally true of non-robot arms too. Like, if I have a robot arm that's like a base joint, if I make contact here, I'm much better at localizing it than if I make contact anywhere here. Yeah. And so, like, if I'm immobilizing my finger, I only have measurements from these things, whereas if I have measurements from everything here,
What would you be measuring better?
probably some notion of force, displacement, the whole thing. Proprioception.
So it could be both then, right? Because you need to measure something. Like slip requires, friction requires some slip in order to take an estimate. So yeah, I'm proposing that, it's that displacement, that slip can only happen if it's allowed to happen. And then what you're saying could be true, because if it does happen, then with all these actuators to measure from, you get an even better information than just being restricted to whatever it's up here.
Yeah, for us, like, we can just have mathematically fluid Jacobians. So like, you basically have a drop in lag as you go back in the arm, or as you use the user fluid.
Okay.
So in the finger, you've lost a lot of the user freedom, and so you have like a drop in lag, but you can correspond to the force.
That's interesting, yeah. Thanks, yeah, good. I think I'm just at the end of this section. Almost. So, this is a very recent paper, 2015, and this is really coming close to the experiment that I want to see done, where it's more like active touch, and the reason for this rail, partly is to control the kinematic, it's linear movement. They have motors, so they can change the load force by turning the motor on, changing the apparent weight of the object. And they have the friction plates on the side, so they can change the friction in real time. And so, but it's a bit unwieldy, and the reason as well for the moment is probably because this stuff gets heavy. It's hard if you build an apparatus that measures everything you want, and then it becomes it's a half a kilo or something that lift it up. It's quite unnatural. So you really squeezing. It's not precision movement. But just bring your awareness to this. So we're kind of moving closer to these natural-looking experiments, and yeah, we do respond to friction if it reduces. So they lift the object up, turn the plate on, the friction changes, and then the response comes. That's a nice experiment. So I talked a little bit about, just there are the limitations. We're trying to build these objects that are a bit more lightweight and so on from Sophie earlier. Here's a previous one that's now open source. If you want to try to build this up, low cost and lightweight, this is the kind of image you get. Just lifting the object up and down. We're measuring force and accelerations. And that's a whole other area like about predictive control. We're not really talking about that here, but humans are really, really good at deciding what the grip force should be if we have good models or prediction of what's going to come. So there's been loads of studies on load, grip load coupling, where you say do something, jump with the object, or you shake it up and down. They're perfectly phase locked. There's no delay. It's not like, oh, I'm waiting to feel the force increase and then I grip tighter because I need to respond. No, it doesn't happen. It's completely predictive. So we know what the force is that we're going to need is, and we get there before it's required, so we don't allow something to happen. So I mentioned that as my discussion that designing experiments to study is sort of difficult because you need to get around that predictive aspect of the control system to try to get at the reactive essential part. So struggling to get to this point where, way back when Johnson was doing that work and they were recording micrometry to record mechanoreceptor responses, they couldn't see the spin, and so I think everybody was working towards this experiment for a long time, and Benoit won the race. So this is the experiment. This paper is now a couple of years old, but I remember seeing it. Great experiment. So he was using his robotic rig to slide glass across the finger, and then he was recording micrography and just showing the relationship between the mechanical events near the afferent, which you could never really see well before, and the mechanoreceptor response. So this is just one video. You can go and read the paper, and there's a couple of videos up there. So the mechanoreceptor here is, I believe, marked. Let's let the video reset. I think it's marked around here somewhere. So around here. So the skin is kind of open and folding, and there's a differential response. It doesn't respond equally in both ways. Their conclusion is that the FA1 afferents in particular faithfully encode compressive strain, so squashing, resulting from those slips, and not so much tensile, which is contradictory to some of the Janssen work, because they were doing some stuff with simple like perspex on mechanoreceptors and did. So I didn't tell you about that part of the story, but they show that it's the other way around. It's tensile. So I think the story is still developing. Yeah, and I remember talking to them about this. Like he was frustrated by the SA ones. He couldn't wrangle them. The FA ones seemed to be just doing what you expect them to do, but the SAs were a bit more unpredictable, maybe like the SA2s. So it's more complex picture. We've gone to read the paper because he's done a good job. Okay, so let's try to wrap this up because I've gone over time. So I think without tactile sensation, our dexterity is worse. At least, don't come at me, for humans, when you take it away, when they've had it and they're used to it and they learn how to use it and you take it away from them, they do poorly. And there's also lots of, if you've ever read that book, it's called The Phantom of the Brain. It's all about what we learned about neuroscience and nervous system from people who were unfortunate to have disease and accidents and so on. And people who lost certain parts of the brain that are responsible for processing that sensory input, they do much worse. Even people that have nerve damage, where their sensory nerves are damaged from the hand, people that have no issues with their motor control, they complain about not being able to do, I can't grab, I can't reach. So like taking that away from somebody is detrimental to their dexterity. Is it absolutely essential? What's that experiment? How do you increase? That's a page for we seem to sense friction very early when gripping. And this seems to be from skin deformation on contact, so some sort of deformation, possibly even slip. And there is direct evidence, which I just showed, that mechanoreceptors respond to this incipient or localized slip events. So the whole sort of chain of sensation is there, whether we use it or not. And how we use it, maybe still unknown. We just grip force very quickly. It's a sort of reflex, not at the spinal level, but supraspinal, very quickly within, say, 80 milliseconds. And the cutaneous mechanoreceptors are not solely responsible for force adjustment to weight. So we see that in experiments with anesthesia, where even we block the mechanoreceptors. And I guess the big picture is like the brain is incredible. The mechanoreceptor responses are very complex. They code all sorts of information simultaneously. It's not just about slip, it's about force, shape, compliance, texture, a whole lot. All goes in and gets disentangled and moves. So challenges in the field, very difficult to measure skin biomechanics. I spent a large portion of the talk talking about all the fantastic apparatus people are building to try to see what the skin is doing, but usually we just image the contact area. It's a very limited view. We talked a lot about skin tracking, the deformation went this way and so on. All of this software, as far as I know, is not validated. Is it accurate? Well, depends on the camera resolution, depends on the algorithm that you use. Like there's so many reasons why the data in the papers could be wrong, not as accurate as it should be, it could be. It's not validated. It's difficult to control texture and friction. They're introducing bias. Texture maybe not so much. Friction is really difficult. If you use agents like oil and grease, it gets everywhere, and it's hard to clean it off the surface, and it remains on the finger, and it contaminates the next control experiment. It's a real problem. That's why we moved to the friction plate, but then that's unnatural. It's a little bit warm. I don't know. There is a risk. Michael and Ingrid say it's not a true risk, but with nonlinear systems, you can demodulate. So you can have a really high frequency of 40 kilohertz. If there's nonlinearity in the system, you can be demodulated down to a frequency that's a linear band of sensation. In fact, they use this to make simulate button clicks, where you click the thing on and it goes through a transition across the frequency band, and you feel those frequencies momentarily. So I'm still a little bit skeptical. Not skeptical, but I guess skeptical is the word. That there could be a bias in the use of those friction plates. All the apparatus are flat and rigid, right? Not very natural. And we didn't really discuss experiments here to do a torque. I showed you one analysis of skin deformation from Sophie. There was a paper by Alistair from a few years ago looking at with Ingrid said a torque and micrography with no imaging. So again, the picture is always partial. And what really torque is understudied. And I mentioned micrography is one effort at a time, really difficult to do. Trying to build an ensemble it is a lot of work. Particularly for slip stuff where it's unpredictable, ensemble methods don't really work. And then I mentioned experimental design needs unpredictability to avoid these predictive control aspects of the nervous system. If you're trying to say, okay, do we respond to slip events? Well, it has to be unpredictable, because if you anticipate it, you're going to respond a priori ahead of time, and already have the grip force scale, and you just, the latency is really short. Latency, it's not a latency issue, it's an anticipation, your anticipation is really good. Okay. So what should we emulate? This is really, me sticking my neck out here. I think in hardware, shear deformation is important. A lot of tactile sensors, which we're going to move into that section soon, and then go probably a bit quicker. They don't really facilitate that shear deformation on the skin, it's overlooked. But I think it's important. We have a dense array of mechanoreceptors, so some shallow and some deep in the skin, which relates to the receptive field, and they respond to low and high frequencies. Now, a lot of work has gone into replicating that, with high fidelity. That's what we have to replicate. I don't necessarily agree. So, do we need that high density? For what applications do we need it for? Maybe not all applications require high density. And do we have to sense it in the same way? Do we have to embed 4 types of transducer in the skin that are shallow and deep and high frequency, low frequency? I disagree that we have to do that. I mean, the idea of biomimicry is like you should probably take inspiration from the concepts and the information that's carried, but don't marry yourself to the implementation. I mean, if you did that, we'd have airplanes that flap their wings, right? And that's biomimicry taken to its extreme. We realised that. I mean, people tried to build those apparatus back when we were trying to learn to fly, but we moved away from that now. We use turbojet engines and fixed wing aircraft. So we need to build the airplane of tactile sensors, not the flapping wing version. Processing, I think we can sense incipient slip, friction, texture, compliance, and so much more. So that should be on your list, depending on your application, which I'll come back to talk about. And globally, certainly we can feel normal shear forces and even torsion. We know from the studies that we can feel that. So maybe these are some of the items that we want to take forward into our central design, which is part 2. So, should we take a break? I'll say 5 minutes, knowing fully well that you probably won't come back in exactly 5 minutes. But, yeah, question. Yeah.
So when about the matches, so
Yeah.
when you try that task without the cues, it's harder to do this. Yes. Could it be because we are used to doing those tasks with the tactile? Like
Yeah.
we have been doing it with
Exactly.
tactile for our lives. So does anyone try to like give them some time, like try it for a long time, and maybe they get better even without the tactile?
That's kind of what I'm looking over. When I was talking about this, but that's exactly my point. That maybe it's not a great example in the sense of you're used to processing that sensory stream, and when it's removed, you feel very offset by that, right? And then you perform much worse than you probably would if you were born without those, without that sensation. Two things to say. One is probably, I don't know if it's ethical to do an experiment like that, where you keep somebody anaesthetized for a very long time and just watch their performance improve based on vision and proprioception alone. But it's an interesting idea that you could do that. But probably it's better to learn from people who've been unfortunate enough to suffer. So there's a relatively famous case of a guy in the UK who lost all sensory input, all sense of touch in his body. If I got that right. They did a documentary on him, and so he's no proprioception, he can't feel anything about the joint angles or anything like that. And yet he's learned to walk. He walks funny, but he's managed to find a way to sort of like keep his balance, and he moves around in a very funny way. It's so unusual, but yeah, that's kind of what you're talking about, that even though the sensory information is taken away, the brain is so incredibly adaptable that you should be able to learn to compensate somehow. Yeah. So that was one example I thought of, and there was another one in my head. It's a good idea, but you just don't know how to implement it, how do you test that. Sorry, any other questions before we, in that section, before we go to the break? Yeah.
Can you just comment on the distinction of why you're using ultrasonic lubrication versus, say, an electroadhesive paradigm for modulating?
Yeah, so when I look, I'm always happy to change my mind when somebody shows me reason to. So when we were trying to explore different ways to do it, we were talking to people who'd used electroadhesion, and they were saying it's not that effective. So we kind of took it as gospel that we've got to make a decision here with limited time and money to build an apparatus, which direction should we go, and the ultrasonic approach looked quite promising. But I wouldn't have ruled out, I mean, maybe someone said, no, electroadhesion does work, and you should use it, then I would change my mind and go that way. Why do you have the...
No, I just was curious if there was something beyond, but yeah, it was more feasible to perform the lubrication, or you wanted to reduce the frictional forces as opposed to increase.
Yeah, the lubrication, that's where we started, as I mentioned, but it's a total mess. Like we use oil, it gets everywhere, so it's actually using like lubricants and stuff like that is not the right way. Maybe changing the surface is the right way to do it, but then you have to control the texture, and that is what we have some samples in the lab for this. It's made by a company in Belgium. What they do is you're quite limited in the texture. You can have smooth or smooth, right? But those smooth glasses have different frictions because at a nano scale, they have different surface topology. So you make different real contact with the skin. So you can have different frictions. The unfortunate part is that the friction differences are not that great. So they're kind of almost below the level that you get friction change from sweating alone, and so the effect that you're looking for is much more buried in the data then. But that would be a nice way to do it, where you just have dry surfaces, so you're not dealing with messy lubricants, and the frictions are very different, and the textures are as far as we're concerned, identical. That would be ideal, but I haven't found it yet.
Maybe you can change friction, you can avoid friction with electrolytation.
Yeah, that was his question, and I was saying, yeah, I think you can do it, and I have no experience with it, so I was told that it's not as powerful a method, so we chose a different way, but it seems everybody else has too. And I know some of my colleagues have gone back to test it and dismissed it, so I don't know what I don't have experience with it, so I don't know what they're really concerned with. Okay, should we take a break? Okay, let's see you back. I want to try and keep you back here in 5 minutes, and we'll get into. So what we probably do is do the usual, where I make myself look bad, and towards the end we're going to jump over about 20 slides. But I don't want to, as they say, stand between you and me. So let's see how we go. I can probably go a little bit faster through this section. So part 2 is sensing. Why tactile sensation? This is actually not a shallow question, because there's discussion about this, and I've had the experience of bringing these technologies to potential customers and asking them if they'd be interested in adopting, and they don't always see the value. They see the long-term vision, but they don't see the short-term gain. Like, what am I investing for? How exactly does it help my business, and so on. But at least in principle, why would we want to use tactile sensation? This is the typical setup for a lot of robotic systems that are using force torque sensing, that they'll have the gripper, probably with no sensation, maybe if you're lucky a little force feedback, usually no force control, grip force control, and then they'll have some force torque sensor here so they can feel interaction with the environment, or maybe you can get it through the joints, enclosures and actuators. So this is the typical setup, and then I'm just going to make a very not very sophisticated argument about why this is probably not enough in all scenarios. And here's a simple toy example where if you were trying to grab an object with a gripper that has no sensation, and you've got a force torque sensor that's feeling the interaction between the gripper and the environment, you'll get your 3 axes of force and torque here. You get no information about contact, so you don't necessarily know how to grab the object. Now, maybe you're grabbing the object tangential like this, and then you know exactly what force to apply. But it could be if the fingers were to be free to change position, so an articulating hand, like a shadow hand or something, you might be grabbing the object at a different angle. In this situation, you would still feel the same forces and torques. You wouldn't know the difference, that you were making different angles of contact with the surface, and therefore you will require different grip forces. If you're using friction alone, if you're enclosing the grasp, don't worry about it. It's not going to, the object's not going to fall when you're enclosing the grasp. But if you're using friction in any way to manipulate the object, it's important to know the friction, the interface between the object and the gripper in order to avoid slip happening, to modulate the grip force. So that's an argument for why we probably would want to have some sensation on this interface, but I would concede and say you could probably get a lot of that information by putting maybe we could have a force torque sensor here or something like that, right? Or you can measure the force. And there's probably ways to instrument the gripper to be a bit more clever, so you don't need to only have tactile sensation. But if the tactile sensor works really well, this is probably an efficient way to do it. So that's my case again. So we would have identical readings, but we would require more force. And also, there might be other information that we want to know, like what is the friction? Is it starting to slip? What's the compliance? What's the texture? Edge detection? Have we got the object in the right position? So there might be a bunch of other information where having tactile sensation would be useful instead of just having a force torque sensor. So now I'm going to take you on it even faster than plan. Whistle-stop tour through history of tactile sensation. So this is this sensor came out probably around 2010, I think, and this was revolutionary at the time. Unfortunately, the company just went out of business. They've been on life support probably for the last 10 years or something like that. I was sort of keeping an eye on them. You know, they had fundraising issues. They changed their business model from, this in the early days, we're going to solve prosthetics, we're going to do robotics. Then they became a materials characterization company, trying to characterize what feels nice to a person. So Mercedes-Benz can pick the best materials for their car without having to do human studies tests, right? And that business obviously didn't go well. The method here is that the primary method is that they have an array of electrodes, and they can measure the impedance between pairs of electrodes. But what impedance are they measuring? They have a sack of salt water, saline, and it's waterproof. And as the pressure goes onto the skin, the cross section of the bag of water will change, and so the impedance between any pair of electrodes, it's like a tomography approach. You can figure out.
It's actually not. It's only to ground. It's not
To-
between
so
pairs.
to ground.
There are 4 ground electrodes, and they're marked with X's, and you get 19 impedances from each of the 19 to ground.
Okay, I see X.
Yeah, those
Thank
are the
you, yeah.
4 ground electrodes.
I
It's
see
not
X1,
pairwise.
X3, X2, X3,
Yeah.
X4. Okay, thank you. Good. But it is impedance. Right.
It's really resistance. What you're right is it's basically the resistance between each of the 19 electrodes, and ground has 4 locations.
Right, okay, thank you for the clarification. And there's also we call it a hydrophone, it's a pressure sensor, so the vibrations, high frequency vibrations, just one channel will travel through the water, that's assuming compressible, up to the pressure sensors. You also get a vibration channel. So really cool, and they moved to this kind of model here, and this became more of a materials characterization sensor, so that was like the beginning of the end, unfortunately. So they never made it. Much more recent, this company I think is starting up in Edinburgh, has raised money, called TouchLab. This method is also resistive. It's a much more sophisticated resistive sensor. It's a conductive elastomer, and they've embedded an array of these. At the moment, I think they can measure shear and normal force, but the sensor they're selling at the moment just measures normal force or pressure at these discrete elements. So I went to the trouble on your behalf to try to find. So here's a picture I found on LinkedIn. It's amazing what you find on the internet. People just put this stuff up there. So I'm on LinkedIn and see, oh look, that's interesting. You can actually see the little taxel elements. So this is for the one robotics recon here. So I went to the trouble to find the patent for you. It's very hard to find this stuff because they don't publish this stuff, so you don't know how it's done. But if you dig deep enough, usually it's in the Western world, you'll find a patent, and it tells you a lot about how the sensor works. So this is, the idea is they've got a protrusion on the top. We're going to see a lot of protrusions in this section, and then they have these conductive elastomers, so they measure the resistance of that. So to get 3D force, which they don't have in those designs, but to get 3D force they would have, which is a limitation of resistive methods. You have to have 4 of them, let's say, or 3 of them, and the protrusion has to sort of like push on one or the other as the protrusion gets moved around, and then they'll compress and the resistance will change on compression. So you can infer then 3D force from the 4 resistance measurements that change. So they're up and coming, doing well, it looks like. This is from Singapore. It's Harold So's group had spin out. They use a resistive method, which I couldn't find enough information on. It's really slender, which is a nice thing about some resistive methods. You can get them to be really sleek and slim. Tend to be a little bit too flat, maybe, and difficult to make compliant. It's a challenge, it's a trade-off. And also, sadly, watching this transition happen where they want to sell tactile sensors, but are now offering a sensor that goes on the lower back for construction workers. So that's a sign that they're struggling to get market traction. The tactile sensor design for robotic grippers, which is Harold Sealy's robotics style. And they're trying to make ends meet by selling into the market where they're measuring probably pressure on the back, and if you're bending over, bad ergonomics, this will give you a warning to improve your posture. So resistive sensing influenced by temperature. We'll probably see that for most electronic-based methods. They can achieve really dense arrays, which is fantastic. Sampling frequency could be limited by multiplexing, otherwise you have to address each individual element. I think that's generally a problem for array-based designs, that you have to either multiplex to reduce the electronics in the sensing area, or you have to individually address each one and read out if you want to read in parallel. That's the design challenge. They could be fragile, like metal strain gauges would be fragile, but maybe conductive elastomers are much more robust, I don't know. It's not published. And shear sensing requires multiple elements, so if you want to do that 3D sensing, you have to set up like the legs of a chair, you have to have 3 or more sensing elements in it that would feel the distribution and the direction of forces. So moving on, a little bit of pressure. So this is Sanctuary AI. So this, the SimTouch, the biotech business that went out of business, Jeremy Fischel was the CTO there, he's one of the co-founders. He left SimTouch some years ago and went off and started this company, Sanctuary AI, where they're kind of in the humanoid space and they're doing all that usual stuff, reinforcement learning and so on. But this thing has always been touch, and they've developed this touch sensor for the distal balance of their robotic hands. So you can see some animation of that there. It seems just to be pressure. Should I say normal force, but it is a pressure-based sensor. So again, I've taken the liberty on your behalf to find the patent, and indeed that's the method that they use. So just to give you an illustration here, I think I've when I put the patent in, last time I did this presentation, I remember, now I've forgotten, but I think it's a fluid that they have in here, in this sort of compartment, and then there's a channel, a conduit that brings the fluid into contact with the MEMS pressure sensor. This would be a pressure sensor maybe that you would measure air pressure in your phone, for example. So there must be a local diaphragm. And so any pressure anywhere here will transfer down this channel onto the MEMS pressure sensor. So we're getting normal force across these different elements, but no shear sensing. And probably good vibration responsiveness, I guess. We're also seeing pressure to floor. So this is right-hand robotics in the very early days. So this is a company that their business model is logistics. So they're packing groceries and picking items out of totes and putting them into boxes and stuff like that. In the early days, their gripper had this design here where if you peel it back, it's just an elastomer on top of some MEMS pressure sensors, so it'll feel normal force. And again, sadly, this is taken from their website. I am struggling to find the tactile sensation in their current commercial product. I can't see it anywhere. They use the suction gripper approach, and they have a little claw that goes around the object to stabilize it, I guess, and it's heavily based on machine vision. But I'm not aware of what they're using for tactile sensation. It seems to be removed, is my point. Why is it not useful? Are they having trouble with it? It would be nice to talk to them. So this is, I think, Rob Hell's behind this, so it's from Harvard, so there's a company that came out of there. They're still going, but I'd like to know if they're doing well. Curious. Pressure sensing, you can use off-the-shelf MEMS, and it's hard, it's a resistive method. If you know how MEMS pressure sensor works, it's a very, 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 very small diaphragm made of silicon, and it has a little resistor made out of silicon also, like an end-up resistor across it, and when the diaphragm flexes on the pressure differential, the resistance changes. So it's actually at deep in its heart resistive method. They also make them capacitive, so you have two capacitor plates. When the diaphragm deforms, as one plate, it will measure the change in capacitance. From a high level, we just take the readout as a calibrated pressure. The pressure sensor cycle is the size within the spatial density. So any of these array-based methods will have that. We have to build like a discrete component on the board. We've kind of got wires coming in and out. We need to transfer the pressure onto the diaphragm. So you have somehow the pressure sensor is usually just a little metal case with a hole in it. It's expecting air to come in, maybe a fluid. So to try to get pressure through an elastomer to transfer onto the diaphragm might be a challenge. And usually just normal force sensing, which might not be what we want. Then moving to magnetic. The idea of magnetic sensors, these are very popular at the moment, is that they have a permanent magnet, not the best diagram, they have a permanent magnet suspended in an elastomer, which is above a Hall effect sensor. So a Hall effect sensor is a little MEMS sensor that senses magnetic fields in 3 dimensions. Well, it's three sensors that sense magnetic field in one dimension arranged in three different orientations. And so you can get a magnetic vector. What's the magnetic field vector pointing through the sensor created by the permanent magnet? So as the magnet moves around, as the spin is deformed, that vector will change. As it comes closer, the field will get more intense. As it gets moved to the side, the vector will change its direction. And you can infer from that the three-dimensional forces applied to the skin to where the magnet is. I'll play this, I think I have sound on this, let Alex talk for himself.
And here we have 368 three-axis structural sensors, and all the measurements are digital, which makes the integration of so many sensing points in the raw hand feasible. The sensors are available in various shapes and sizes. So here we have 1 sensing points, 2 sensing points, 2x2 to 4 sensing points, and 4x4 16 sensing points. We also customize the sensors, and for example, in this case, we have 7 points in a curved fingertip shape. And then we also have to use the multi-band, and in this case, the sensors can apply to curved surfaces.
So the limitations of these sensors potentially are that it's a passive method. What I mean by that is that the magnet, we don't have control over the magnetic field, so we can't pulse it, modulate it, do anything to let us know that this is the magnetic field we want to measure versus all the other magnetic fields we don't want to measure. And so if you brought a magnet into the proximity of the device, I would expect it would be perturbed by that permanent magnet. There's also a risk of ferromagnetic materials. They don't carry a magnetic field themselves, but they have the propensity to distort that magnetic field. So the magnetic field in the vicinity of a conductive material like iron would distort, so it has to align with the surface of the metal. And so that could distort the field of the permanent magnet. But we were I didn't realize we were talking about humans using these sensors, and so they seem to be quite well shielded from at least ferromagnetic effects, which leads me to think they probably have what's effectively a Faraday cage, so like a metal coating on the rubber somehow, that's my guess, to try to shield external ferromagnetic effects. But I don't expect that it will shield from permanent magnets. So that's a challenge. There is a risk that they give erroneous readings if they're brought into contact with iron or with other permanent magnets.
And here we have
They're really, really popular at the moment. They do really well. It's a growing popularity. One of the most successful commercial sensors, Zila, which, if you're wondering why, the guy's name's Alex, so it's his name backwards, Alexander. Zila Robotics, it's 3D sensing, very thin, which is appealing. The density is limited, so I think their pitch is 7.5 mils between sensing elements, so nowhere near what the human hand has. Susceptible to magnetic interference because it's a passive method and requires temperature compensation. I know that's true because they talked about
What are sampling rates like? Sorry?
Sorry?
Temporal sampling rates?
I think they're getting up into towards the kilohertz, probably, is my guess. A lot of these electronic methods, because if you can not have to hold them, if you have them reading, they're all on digital line, you can read at quite high rates. You can get up into the miles of kilohertz. Which is all, we'll come to camera-based methods, you'll have to see it's quite the opposite. So, I don't know, I think it's in the ballpark of 1,000, it's certainly a couple of hundred hertz anyway, but it will be well above camera-based rates. Oh, and I should mention as well, I'm trying to go fast, but then not skip important points. When they first started this company, they were just selling sensors as, you get the sensor and it gives a readout, it's a voltage. What does it mean? That's your problem, we figure it out. What does volts convert? What's the units of the volt representing? Is it force? Is it pressure? It's whatever. It's just something right. So then, and that's what they would sell. That was fine because it was the only shop in town. So that's what people buy. They calibrate themselves. And then with competition coming into the market where people are selling calibrated sensors, then I think they realised the value in that. So they responded, and now they have different tiered offerings as far as they know. So you can buy an uncalibrated sensor. Saves them time because they don't have to calibrate it, they sell it to you for less. You can buy a calibrated sensor where they put it on a test rig and they calibrate it up for force and so on, ensure it's not drifting, and then they sell it to you for more. So you get what you pay for. But calibration might be important to you because maybe you want to work in SI units and you don't want to have like volts, whatever that means, going into your control algorithm. You want to actually have, millinewtons or micrometers. So then, try not to do any service to it. So then we have camera-based sensors. So like camera-based approach has been around for quite a long time. The guys at MIT, I'll come to gel site next, because actually in chronological order, the sensor I'll show here is a digit. So Roberto, you're deeply involved in this project. Yeah,
That's my baby.
that's his baby, and so the whole idea here was to sort of bring this to the world and make it available, make it open source, and before it was all academic. So the gel site people who were, the history there is that I'm aware of is that gel site came from MIT, at Alston's lab in MIT, and he's a vision guy, and so they're building tactile sensors using vision. And then grad student from his group went out and started a company gel site, and their main business is meteorology, so they have a camera-based method that looks for cracks in metal, so they use it on airplane wings and looking for fatigue and fracture. Never really tactile sensing in the robotic manipulation space, but to overload the name, the graduate students who followed behind would start to work on tactile sensors for robotics using the same principle, and they would also be called gel sites. You see all the academic research, gel site 2, whatever. And they never made a commercial until quite recently. So this is a camera-based approach. They're all very similar in the sense that there's a camera, I assume like a smartphone camera type is used, and then there's some sort of lens which would separate the camera space from gel skin. The idea is to just look through the camera at the deformation of the skin and infer tactile information from that. So yeah, there was people modify. So Nathan before I took, you were kind of gifted us a couple of these when this launched, and then the very first thing Nathan did was tear the skin off and put his own skin on it. So because he wanted something, he's like the things, and it's like that's fine, creative. And then gel site followed very quickly behind, because as the story goes, I think you worked with gel site to actually, they were the distributor or the manufacturer distributor of that digit. But then very soon afterwards, we saw the gel site mini came along. It was on the website alongside digit, and we were on the motion. So I guess the gel site decided maybe people are buying this, and I'm guessing they decided to sell their own version. So these sensors they have like incredible spatial resolution. I think it's unrivaled. There's no tactile sensor that can do spatial resolution like that. Whether you have to do it with a camera or not, or whether you even need that spatial resolution, I don't know. Maybe for some applications you do. And then there's of course a bunch of limitations with that. There's more of these. So this is Digit 360, which kind of solves the limitation of a lot of these sensors being quite flat skin. Which pretty much all the sensors we've seen so far have been nowadays. And here they have, I'll show you the diagram on the next slide. It's more of a fisheye lens, and it's the same principle. You're looking at all the skin from inside to all around, so you can feel sensation in motors, which I think is very important actually for manipulation, especially blind manipulation, where you have to feel contact not just on the object, but we're assuming that we have the object in the grasp. There's a whole phase of motor control that comes before that to establish the grasp, and you might be reaching into a tote, and there's objects around you have to nudge out of the way, and you're going to make collisions. So you want to feel sensation on the back side of the hand, not just on the inside of the hand or on the side of the fingers. So this is the right idea here, to be able to feel on all sides. And that's what it looks like. So very sophisticated. Silicon fingertip, fisheye lens is here. Lens that goes all the way down with a bunch of data processing stuff embedded as well. What kind of worries me a little bit is that I saw the air intake fan and I thought, wow, is this thing generating heat? Do you know much about it? Does it generate heat?
Yeah, sure.
Yeah, okay.
I can give you a demo. So in this moment, the image signal processor that we use is oversized compared to what we need. Okay. So it gets really hot. Okay. But we also remove the fan, so it's now only passive. Okay. In the future, we will use the right size of image signal processor, and it will be a little bit
cooler. Yeah, but I guess I'm trying to be critical here, right? And I'm saying that one of the limitations of camera-based methods is that they are so computation intensive. You've got to receive a high resolution, high frequency image. and you have to take features from it. You've got to do some work. And that comes for free, almost for free with a lot of the non-camera-based methods because each element is discrete, so it's already localized, and it's a very simple algorithm, but we pay other prices there. We don't get the resolution, and we have to do all this complicated electronics, whereas this is very compact, so it's really pros and cons. This was from real research, so the same idea. This is a big Baymax type fingers. Again, tracking dots so they can measure deformation with the camera on the inside. They're doing steps of machine learning. I mean, these guys are more interested in what's the robot going to do and intelligence part of motor control. And so much tactile sensors more needs to an end. So that's pretty cool. And then quite recently as well, Shadow got into this space. So I don't know about this one. Like, I've seen that I've some of the composites and that, or had a look at it. I think from an engineer point of view, the hand is cool. So like the story behind the hand is that they were selling their Shadow hands, which is a previous version, very expensive, about £100,000, selling them to DeepMind to do deep reinforcement learning. They would set up Google, so it's a big bank of robots, and they're learning how to do manipulation tasks with a Shadow hand and some robot and all the deep learning stuff. And they had a big bank of them and loads of money. But the hand is notoriously fragile, it would break, and then they would call the Shadow, and your hand's broken again, please fix. And then I think they got into an arrangement where they said, look, just build us a better hand, and we will pay you for it. And this is the hand that came. So it's modular in the sense that you can disconnect any of the three fingers. It's very robust. I think they were testing it, like cycle testing it, and it was the testing actuators that broke before the hand broke. And they've also got this, what's an active control, so you can hit it with a hammer, and it doesn't just passively to move out of the way, it actively retracts from the hammer blow. So it's very robust, that's fantastic. I'll show you again in the video because what they've gone for is, in the distal phalanx they have a camera-based approach, but the skin seems quite rigid to me, and it's flat, and it doesn't seem to want to undergo shear deformation very much. It's even hard to see manipulating this little match box here. What's changed? I don't know if they made it a little bit yet.
How much is this?
The hand.
Yeah. I don't know exactly, but I'm going to give you a ballpark. Like they tend to sell stuff in the order of like tens of thousands, so probably 30,000 to 50,000.
That's more.
80.
And it's huge. It's like the size of my forearm.
Yeah, you can see the chest pieces here. Yeah, it's a whopper. Like it would be, I mean, this part here would be like that big, and that's like the wrist of it.
Is it because it's cable driven?
Yeah, they've got cables and motors and stuff and all that in there. And it's totally modular. That just slots out, and you put a replacement in if you do manage to break it. But also they've gone for magnetic in the other phalanges. So like in this one and this one, the second, third phalanx, they have magnetic sensors. I'm like in a dense array of 14, but then the skin is a lot hard. So I don't know why would you put such a dense array into a skin that can barely move. I know I'm being a bit unkind, but it's just when you see it and you just can't rationalize why you do it in that way.
It's because the magnetic interaction length is super short, and so you need actually a pretty stiff layer because even small distances give you a big signal.
Okay.
So you have to adapt the stiffness to the interaction length of your interaction, and the magnetic that can be super.
So you can't allow it to be more compliant or it get saturated?
You could, but you lose.
That's good to know. So that's Shadow. I think for this one, they built it for DeepMind. They probably got it as a contract, and now they can try and sell it to other people. I don't know if people are buying it. I'm not that interested. Okay, bear with me now. Vision-based sensing, incredibly powerful. Very popular in academic research, really popular. Like if you go to ICRA, there's a whole session just on vision-based sensing, and all their tactile sensors be gone. We don't want to know about them, so it's a bit sad because I'm working in another area that I'll talk about now. But I think the reason is that it works. You know, like if you don't care about all those practical implementations about going to industry and making it work, you can get a lot of really rich information really easily with established technologies, and you can do all the other stuff you care about. You want to do deep reinforcement learning, robotic control, just do it. Like, and it's probably not going to make it to industry because you've got a vision-based system that's just not going to make that jump. But you know, why? That's not your problem with it. So easy to build, robust to most interference, I would say. Not known for the durability. These skins tend to tear, notorious for just not being durable. This is one of the other reasons why I wouldn't have made it to industry. Unrivaled XY sensing and generally resolution. I think force displacement, I think I've seen people, oh yeah, we've solved force displacement, the Z problem. I don't think they have solved it that well, probably is my guess. And I've even seen designs where there's stereo vision. We have two cameras looking at the skin from different directions, trying to triangulate how much it's been pushed. Because it's difficult with a camera to look at something when it's far away and know it's moving towards or away from you without enough parallax or displacement between reference points. So I'm a bit skeptical about that one. Gelsite uses some, at least for small relief patterns, they use a stereo photogrammetry method where they have lights with different colours shining from different directions, and then they have different channels, so they can sort of see shadows created by little patterns that pop up, where a pattern will pop up, and the red light will be blocked and pass the shadow this way, and then the green light will be blocked. And you can infer sort of small relief patterns, but I think large forces are tricky. I think if they expect too much data, we just had a discussion about the sensor trying not to melt itself due to the amount of data that's coming through and has to be processed. If you try to process on the edge, so you need video processing, and you have to transport that data around if you're not going to process it on the edge. And yet, no sampling frequency. So, like, let's say 120 frames per second if you're lucky, you've got a good camera. Whereas some of the other non-camera based sensors are sampling in the hundreds or thousands of hertz. And human sensory perception goes up to, let's say, somewhere between 500 and 1,000 hertz with the field vibration. So you're going to get aliasing maybe for a lot of contacts. But people are using event-based cameras, so I'm doing some work. George is down there, all the George keep going. And he's working with Ben Cherry, and I'm doing some collaboration with them on this as well. So event-based cameras are one solution to this. Not ideal in that they only, like a T-Rex in Jurassic Park, if you're old enough to remember, if you don't move, we can't see you. And they only respond to change, so they can pick up transient events, but not. They couldn't look at a static scene and see anything. They only pick up movement. So that might not be great if you're trying to measure static events. Doesn't make sense. Static properties. But the idea of an event-based camera is purely asynchronous. The pixel will only change when its intensity changes from high to low or low to high, and that's the only information that gets sent. And if there's nothing happening, there's no data. So the data rate's much, much lower. So maybe event-based cameras will save region-based cameras. Potentially limit the coverage area. You can only measure what the camera can see. So if you want to cover the whole body, this is not the technology for you. So it's really just limited to a phalanx. But what if you want to do the whole finger and the palm and all the rest? Are you going to use cameras for that? I don't think so. And they tend to be quite thick because you have to keep the camera. There has to be a focal length between the skin and the camera lens. Otherwise, you can't resolve the image. So people have used all sorts of clever tricks. We have fisheye lenses, we have folded optics where you would send the image around the path to shorten it, like they do in telescopes. But please. Challenge.
So I think the digital physics resolves a lot of these problems, but 2 points that I think, generally speaking, I do not fully agree. So, regarding the durability, I think that the problem with durability is not intrinsic to the technology, is more connected with the way that people currently build these devices. It's really the fact that most of the people that build these devices are computer scientists, You know, no, not material scientists. And just to give an example, the digit mini, if you apply any type of shear forces, it will delaminate. Like, you can throw it away. And the reason is because they use a process which basically rely on using either silver or iron powder, and then they basically cast this on top of the silicon. It does not adhere at all. At Meta, the formulation that we designed for digit instead was designed very differently. It's actually spray painted, and you can easily go up to 10,000 grasp and more. So it's really the fact that
Yeah, I do agree. I mean, it's probably unfair to single out vision base for this. I guess historically they have been known for this issue, but it's a general issue. Like any sensor that has an elastomer on top of some, usually some sort of hard substrate. It's a sulfur-based problem. How do you make the salt and the hard meet and not come apart and tear? So I think I agree with you. It's a more general problem. But yeah, and even even thinking that like, some of the designs I showed coming up with the pillay and like protrusion and so on, we use clamping methods where we like poke holes in the top plate and clamp down the skin, and you could do that for a vision-based camera too, and just leave the bits sticking out that you want to move and measure them. So there's probably ways that you could get down to get up to the robustness of a non-camera-based sensor. So it is a more general problem.
And I do agree in general that this is a problem for all tactile sensors, because until we reach the sophistication of organic skin growing back, every time that you touch something, you have where
self-healing. There is some work, and I talked to about recently, so we're often tangent, but yeah, like metal materials, and people are doing stuff with this self-healing material where you just warm them up and they melt a little bit, and they go back. They more or less restore themselves. That was a cool idea. They have self-healing elastomer. And yeah, it would be good if the materials people would get involved in this a bit more, because I'm an electronic engineer. I'm building mechanical stuff, so I'm already out of my depth. What do I know about materials? I don't know. I'm thinking about vulcanized rubber, but I don't know about vulcanized rubber. It's going to be too tough, and can you vulcanize it? That's what's on car tires, right? It's very resilient. But some material scientists know how to do this stuff, and they'll look at this problem and say, oh, you're using the wrong stuff. Don't use that glue, don't use that process. So, yeah, it would be good to get them involved. So you had 2 points.
Yeah, the second point is regarding the Z-force.
Yeah.
You actually can get pretty good Z-forces. Again, it depends a lot from the optical system that you use and the illumination. But with DG360 we have millimeter.
And is it, what's the mechanism of this? If you're looking at like 2 reference markers coming closer together or further apart as it comes, you know what I'm talking about? Where there's the apparent distance between them would change based on the distance to the camera? Or?
So the way that we perform this evaluation is that we basically use machine learning to regress to what is the interpretation of the force. But in practice, what's happening is that we have a resolution such that we can pick on. We don't have any type of markers. We just have normal coding like JetSet does. But we have a resolution such that we can see the imperfection in the coding process. So you basically have this texture, and you can see how this texture is moved. And through machine learning, you can basically do it.
I stand corrected. I removed that from the talk in future. But it had, I think in the past it had been a challenge, but it sounds like it's solved.
Again, I don't know if this is a problem with some particular sensor or more of a general problem.
Yeah, it sounds like it's solved. Okay. That's information. So we got to move on. Optical. So optical, I guess camera-based are optical, but I'm just distinguishing them from non-camera-based optical sensors. This is a company in China. You may or may not have heard of Maxini. Just blown up out of nowhere. It's just a humanoid hand, and they have optical tactile sensors, and I think the family came out of the same lab at Waseda University where Alex and Zila Robotics came out of, and went off to China and raised an absolute ton of money, and is now selling or trying to sell these devices. So I also found that works, which is almost impossible to find. There's no patent, there's no academic paper to borrow one. I found it. It was written in a Japanese symposium sometime way back in 2017. It's an optical method where they have, I don't know exactly how it's implemented, but they have an array of LEDs and they have an array of photodiodes, and as the skin is deformed, you ask the LEDs come closer to the photodiodes and the light intensity will increase until they can infer pressure and force. I don't think they can do any shear displacement. But the technology looks pretty cool, and they seem to be understood. And something I wanted to show, which is a video they have on their website, which is sort of what we've just been talking about, durability. But yeah, it is a general problem. And what's nice to see, or at least they recognize, is that customers care about this. So they're doing testing. So it's IP68 rated, they say, and they're doing durability testing on this. What's that piece? Electromagnetic compatibility testing, corrosion resistance testing. And generally, this is not done. And then customers will say to you, if you try to sell it to them, like, it's been characterized in these ways, and say, no, I haven't done that because we can't afford to do it. Give us some money, we'll do it. So yeah, it's important to do that kind of stuff, and it's nice to see that we're doing that directly. So. Then we have Tesla bot. I don't know, I just put this here because, you know, Tesla is a big deal, and it was this very small part of the demo video, and I saw hands, it has hands, and it has tactile sensors, so I got excited. And I went straight to the website, I went to that, and I couldn't find any. I still can't find any information. I don't know. If anybody knows, please tell me. What are they using?
I can tell you over here.
Oh, he knows, okay, good, right. Straight for a beer after this. My guess is probably capacitive arrays or magnetic arrays. Okay, so yeah, I think I'm going to end up skipping the last part of my talk. I'll show you one small bit of the last part, and then we'll finish because we're going to go over time in this launch anyways. So back to the incipient slip sensation. This was a concept, as I said, we're working with wing bars, and then I won a fellowship to work on this problem of building an artificial sensor that could feel friction the way we, at least hypothesized humans could feel friction, which is through incipient slip sensing. So as a first approach, we thought, well, let's build a finger pad that kind of least experiences shear deformation. And one simple way to do that is to just take a lump of silicon and cut it up into discrete elements, and those elements can move relatively independently. And also we create a traction profile by differential by making the pillar in the center the tallest, and the other pillars progressively smaller as you go to the edge. So it has a contour like a finger pad. And then when you put it onto the surface and you drag it to the side, exactly what you think will happen happens. So the center pillar is the last to slip, and the ones on the small ones on the corner, they pop up first. You get this incipient slip pattern coming from the outside. It's very crude. You even see like how do we stick, again, self robotics, how do we stick the silicon to the 3D printed parts? It's stitched. He's stitched like cat cut that you didn't use to. It's like this is really rudimentary, but a very, very, very first prototype. The reason I show it, warts and all, is just to say to you, like, when you see really sophisticated stuff in research papers, don't be daunted by that. It's just all of these things started as really scruffy, messy prototypes. You just build your first prototype, however rudimentary it is, and then iterate from there. Right? So we thought, well, the square edges are kind of digging in to the edge of the glass, so maybe we should smooth the edges a little bit. And the landscape's a little bit soft, we'll go for a harder pinky sill. And then we had this one, which I was calling the cow's udder, which didn't go down well. And then somebody said we should call it the raspberry, so it became the raspberries for a while. It got rebranded later. So the challenge then was, okay, we kind of have a mechanical proof of principle, very rudimentary, and how would we instrument the movement of these papillae, we started to call them, what would we use? And I had master student Ben, who joined the team, and I said, look, this is my challenge. I want to measure the movement of these things, but I don't want you to use strain gauges because they really just flex in one dimension and they're going to cut the silicon apart in the other direction. Don't use magnetic because I'm worried about interference, and I put a few other constraints on him and he went away. And he came back a very short time later and he showed me this demo, or a demo similar to this. In fact, the very first demo was a rolled up piece of cardboard with an LED and some photodiodes, but this was like a next generation demo. He's only instrumented 2 in this early prototype, and he's just trying to show the XY deformation that he's measuring, and if he pushes down, he has some measured force. So this is like early stage development. We thought we had something interesting, and I still haven't told you how it works. But I was impressed by this. I thought, wow, you've done a good job. How did you do it? So this is the method. We use, this idea is actually used in several alignment methods. So I think we were talking around about being used in microscopy.
Atomic force microscopy.
Yeah, so it's used to align things in microscopy. It's also used for satellites to orient themselves to the sun. And the idea generally is you have a light source generated somehow. We'll talk about how in a moment. But you have a light source. It comes through a pinhole and makes an image. That's what's known as a camera obscura. If you've ever looked at an eclipse through a pinhole in a cardboard box onto a piece of paper, you see an inverted image of the eclipse. It's a camera obscura. So we have a camera obscura that takes an image of a light source and inverts it, and we capture that image with 4 photodiodes. You can buy them as a package. It's called quadrant photodiode. And depending on the movement of the light source, from the 4 measured photocurrents, you can infer the position of the light source. Now, what is the light source? In our case, it's a reflector, and it's a diffuse reflector. It's not like a mirror. You couldn't see yourself in it. It's like as reflective as the white paint on the wall is reflective, and the rest of the silicon inside the sensor is black. So it's all black. Most of the light gets reflected, scattered off the reflector, and absorbed somewhere, but some of it comes through the pinhole and makes it to the photodetector. So this is what it looks like. We've got 2 LEDs just to make sure the reflector is always covered in light. A pinhole and a quadrant photodiode. So that was a very clever idea, I thought, and we patented that. And just to give you an idea of the sensitivity, the setup here, just so you understand this, we have just a single pillar. We have the 1 of the photodiodes of the 4 going to an amplifier, just and a little bit of filtered, so you can hear it. You want to hear the sound, hear the touch. Sorry, pause that. Instead of showing you a squiggly line of the sound signal, you can just hear it. So the idea is that we're vibrating the pillar, the little reflector is shaking, the little spot of light is moving, and the photocurrent being generated is operating in the amplifier, you can hear it. So it's very sensitive to vibration in addition to those static forces. So we started a company. I have to say all the work was Heather and Ben. I was still in full-time employment, so I was adding my 2 cents and supporting them as much as possible. And it was a long road. There's a whole story. I could talk for an hour probably just about this experience alone, about trying to found a company and trying to raise money, and it's a challenge. And the biggest challenge that we faced was trying to identify a customer and a killer application. That's the challenge most businesses will face raising money. You got to go to an investor and say, you don't go to them with technology, you go to them with a problem. I have a problem. I've identified a problem to be solved, that people will pay money to solve, if I solve it. And on top of that, I also have an idea about how we might solve it. If you go with those 2 things to an investor, they'll probably give you the money. Even if you don't have the technology, just you've identified the problem where people will pay money and you have an idea of how it might be solved, you're going to get the money. Don't do what I did, so I went to my first venture capital pitch and I gave an academic presentation, pretty much as you perceive today. Humans feel friction, it's really incredible. Incipient slip is so important. We've got a technology, look, it can do, and then can I have some money? And he's very polite, and he said, well, next time you give this presentation, start at the end. Start by telling me who has a problem, how big the problem is, how much money will they pay for the problem to be solved, what do you think you could do to solve the problem, and then maybe tell me about the technology or not, I don't care, I'm not a tech guy, you know. So I left the place a little bit embarrassed and humbled and grateful like for his advice, and I never made that mistake. So the company did raise money a few years ago, raised about $4 million, and then they're trying to make that transition now to their Series A. So I left the company in 2022 because I'm still a full-time employee at the university and also working on technologies very close to what they're doing, so it gets a bit, I don't end up in court and lose my home in a settlement, so I exited the stage of that. But anyway, I'm very proud of what we've done and what they continue to do. And I'll just show you some video examples, which will bring us close to the end of this section. So the nice thing about this, I guess, on all these array-based methods is they are reconfigurable, although with some effort and work, you have to redesign the circuit board. Then you can build single elements. They sell a little button sensor like this that measures force in 3 dimensions. That's what you want. The embodiment can change. So of course, this was in collaboration with it didn't go forward, but it was Tasca Prosthetics in New Zealand. They make a waterproof myoelectric hand, and they were looking to put sensor touch in, so they did a little pilot with them to show that it could fit inside the distal phalanx of a small prosthetic finger. So again, just 3 dimensions of force, this one sensing element. Again, just to show that this is down onto an array, so you've already seen a demo like this. So here he's playing a piano app out of the speaker. It's too quiet to hear, but if we amplify the touch sound, touch can feel the vibration, and if you amplify that, you can hear it, right? So it's very sensitive to movement, which is nice. And then this is like a long demo that they did recently where they're just showing, we started to build these into arrays, which was the original goal anyway, to build tactile arrays and feel friction instead. They're just showing some of the capabilities. So yeah, you've got your sensing, and if you do, I'll show you how we do some of that stuff now shortly, but if you do friction estimation on contact and you have brute force control, you can just go and grab stuff and just adjust the force automatically. So not, they call it Goldilocks grip, like not too light, not too heavy, not too hard. There's a whole vision part of that. I wasn't involved in this, but I just showed you. But then there is a new way, which is the reason I left the company, because we were developing new technologies at University College Dublin. So I always thought that having the pinhole method was making the sensor just a little bit too thick. So I had an idea to use, instead of what you normally see, everything else is the same. We have some LEDs, we have a cavity, we have a reflector. Everything's black, the white reflector. And normally there would be a pinhole here, and below the pinhole there would be a quadrant photodiode. But we just removed that and just put in, this is an off-the-shelf component made by Analog Devices. It's a light angle sensor. And so just with this light angle sensor, when the reflector moves around the direction that the light returns, this is a pseudo source, right? It's just a reflector. So it looks like a little white moon in the sky. When you deform it, the light will change its direction, and when you bring it closer, the light intensity increases. So you can infer 3-dimensional displacement and force just from the angles and intensity of the light landing on this. So this was the work of a Ph.D. student. Olivia just graduated. That was her first prototype. Just a single element, so achieving the same with a thinner design and off-the-shelf components still. How do we, I might skip a bit more quickly through this, but we do calibrate all these sensors, same for the tactile. The way that we do it, there must be a better way to solve this problem. It's quite time consuming, but we would put the sensor on an HDI 4-stroke sensor, and then we would mount that on a controllable stage, and we would push the sensor into a plate. And there is a risk that the sensor will slip on the plate, so we also have to measure the displacement of the top, so we can subtract that displacement from the robotic stage, and we get a reference for displacement, and we do regression. So that's it in short. You just see how small the movements are. You might not see, but this should be playing, and the robotic stage is swiveling around there. And there is a risk that the white slip tracking that will slip, and then the camera would detect that and would follow it, so we subtract it off. But it's good, it's calibrated really well. We're getting like tens of microns of precision and in the displacement, and similarly in the order of tens of millinewtons in force in 3 dimensions. Nice. And then of course, yeah, you build one, you make an array, seems to be the next step. So she's making arrays, but still a little bit rudimentary. It's just a circuit board, needs the big screws that shouldn't be there. You can see these elements here. There's the photo detector and the 2 LEDs, and then the skin just sits on top of that, which is a limitation. Like I say, I'm not a materials person, so there is a robotics problem. How do you make the skin join the electronics in a robust way? At the moment, we just put a top plate on, so we get a piece of plastic, cut holes in it for the little pillars to go through, and just clamp it on. There has to be a better way. So this was originally designed for the RG2 gripper. Why not? Just to see if we could. And there are some challenges with this, which I'll disclose. It's just probably the nature of all mixed electronics, so digital analog design. If you have any experience with that, electronic engineers might know. It's very difficult to build systems that are digital analog, especially low voltage analog on the same board. If the currents in the ground there cross over each other, they interfere. So you've got to be very careful with placement. And we did have trouble, not in this design, but in another design the student did, where one pillar was especially noisy and was probably passing too near to a digital line. And that's a challenge of building these things. Like having all the electronics on the board is an issue. So you might want to think about moving the electronics elsewhere, but then noise contamination and stuff. So look, I'm not saying that array-based sensors are the answer versus say camera-based, but they have their pros and they have their cons. And I think signal integrity also is a risk if not designed right.
Can you explain it again one more time?
Also, yeah.
Yeah, but what is the discrete thing that you're measuring?
So, yeah, sorry, so that's jargon, but some digital circuits might have digital electronics, so it tends to be stuff like clock signal, which just goes 1 0 1 0 1 0 1 0 really fast at megahertz, and then they'll pass information to each other as digital signals, like this line, a read line goes up, goes down, goes up, goes down. So these like big changes in voltage at like 0 to 5 volts or whatever are happening. And those currents, because the circuit always has to be big, the current that comes through what's called ground plane. It's like a big ground for the circuit, and those currents will flow across. And if you were then to put, try to pass an analog signal also passing through the ground plane nearby, you can get contamination of the digital line pulling the voltage of the ground plane near to your analog. So the best design practice is you put all your analog stuff down this end, you put all your digital stuff down that end, and never the twain shall meet. So it's just a challenge when you're limited on space and you're trying to pack everything in to not have those lines coming too close to each other. So there's a couple, even capacitive coupling between 2 wires close to each other, one wire changing, and then pull the voltage on another. It's a big problem in integrated circuit design where things are on micro and nano scales and you get wires talking to each other. So they do a lot of simulation. That's the Synopsys of the company, because they simulate micro integrated circuits to test that there's crosstalk. You know, it's called mixed signal design, and it's a big challenge to try to build digital electronics and analog electronics on the same chip without them, particularly the digital, interfering with the integrity of the analog signal. Does that make sense?
Yeah, that was awesome.
Yeah. But then all this stuff is flat again. So, did you?
Sorry, I have a question. 3 years ago, there was this company that was producing octoforce. They were acquired. What's the main difference between Librec and octoforce in terms of concept?
The difference is so Roberto was referring to a company that I think was Hungarian, and they made 4-stroke sensors and tactile sensors. And their method was, like I can describe it was similar in that they had a dome, and they had a light source in the middle that would shine light through the whole dome, and they would take reflections from the entire dome and actually put a lot of effort into getting the reflective properties of the dome bright, such that if the dome was deformed or displaced, the light returning to 3 different photodetectors around the light source, the amount of light coupled into those 3 detectors would change in some way. So the difference is that the sensing is distributed, and that they have these photodetectors that are distributed around which is not too dissimilar to the quadrant photodiode. but they're using reflection of the entire dome, whereas we are isolating a small patch at the top, at the top of the dome, and the rest of the dome should be black and absorbent. Does that make sense?
And is there an advantage or disadvantage between the two?
I think the principle is different, and that's the question is advantage or disadvantage. I don't know if I were to calibrate their sensor and our sensor, would they be on par, or we would do better, they would do better. But in principle, they're different in the sense that you're getting displacement from a much more complex reflection field, you want to say light field across the whole dome. And I couldn't explain to you intuitively exactly what's happening when they perform it, whereas the method we're using, I'm telling you that we are trying to localize a spot, a light source in the air above the reflector. Here's the mechanism we're using, it's to catch the spot or to find the direction of the light coming back. So I think the mechanism in principle is different, but whether one's better or worse, I don't know.
Apologies, this was a very tough question. As a user, there goes round.
Yeah, and people have said to me, it's not the first person, that's like optoforcing. But they got bought by OnRobot, and then I thought that they became a part of the OnRobot 4-stroke sensor, but I was told recently that that's not true, that they use resistive sensing. But again, this is gossip. We're just gossiping about what's that company doing. So I don't really know. What they use. Sorry, I know we're coming to 12, so I'm going to try and wrap up this section and then we'll.
We can also continue in the hands-on session a little bit, if you
Or if I go, do you want me to go overtime now or just
No.
want. Now
There's a lot of people out.
Yeah, so we should go for lunch. No, let me just finish the section and I think I'll leave the other part. The other part was on algorithms for slip detection and stuff. So maybe we can decide over lunch.
We have speaker 7 on Friday, right?
Yes, that's also another
Or I could do, I'm here on Friday, I could do another slot on Friday morning. Yeah, well, we can chat about it over lunch and whatever people want, we can adapt. Yeah. Sorry, I wasn't sure on timing, but I knew in my heart I had so much to say about every slide that this would never be good. So what about non-flat surfaces? Like, how do you do that? And you saw it for the Zeal robotics. With printed circuit boards, you can get flex PCB, so it's a flexible circuit board, but it depends on how many layers you have. It can be quite stiff if you put 5 or 6 layers in, so it becomes a challenge. But we've had a couple of mock-ups where we've done little curve sensors that can curve and test their calibration. Unfortunately, calibration doesn't survive being flexed. You can calibrate it flat and then you flex it and put it to work, and the calibration is not true anymore. So has to be calibrated in situ. And then you can do stuff like, imagine you want to cover the surface of an orange, you would imagine peeling the orange skin off, and that's the way you would build the circuit flat, and you would wrap it up. Okay. Challenges, we talked about making skin. We started to, we hand molded everything, which is the most time consuming process, really time consuming. Started 3D printing, this is off a Stratasys, but the materials are not great, not very flexible, so I still don't know the right way to make the skin or how to bond it. Temperature compensation, it can be solved. It is true for all optoelectronics, they're temperature sensitive. LEDs will drop their output with change in temperature, electronics on the board will change, resistors will change, so it's hard to get a stable reading. You need a temperature sensor on the board. But there are other ways that we've been exploring. This is not published, but maybe using multilateration, where you have multiple sensors and then you can sort of see where the 3D position is without needing to know the intensity information. Okay, so optical sensing, very sensitive and accurate to within microns and millinewtons. But it has a temperature issue, and we talked about mixed signal. Very high bandwidth, so you can hear all vibrations, very nice. 3D sensing is easy enough. Can be made relatively thin, which might be useful, but density is an issue. So it's a trade-off for all the ray-based sensors that it's hard to get them packed in really tight, and they end up being relatively low spatial resolution. And this is the bit that I'm not expert on and struggling with, but making the elastomers and making them join the electronics so they don't fall off. And I think this is the biggest problem that has to be solved in some way, because we've been talking a lot about what Amazon wants, and they want sensors that don't fall apart after 100 iterations. Okay, that's the end. So sorry we went out of time for part 3, and so we'll discuss. Maybe I could do Friday morning if it's free. I don't want to take away from the hands-on. So.
I think it will be wonderful Friday morning.
Yeah, let's do that. Okay, thanks for your attention. Should I say any questions before I finish talking to 2 hours before we go through? Yeah.
For the last part, we see the plus Excel with the interlocking material system.
No.
So you can combine soft TPU with hardness PLA and mechanically interlocks them when you slice it.
Oh, so it's like a hard soft material that mixes
Yeah,
together.
I've been using that to combine just TPU materials.
And that's printed on a stratus or something?
No, it's a plus Excel. So it's
Plus Excel.
multiple toolkits.
Oh, so it's actually affordable. It's supposed to make.
It's around $4,000 with everything.
Yeah, that Stratus machine cost me university $7,000.
Yeah, so when
that's a low end printer for Stratus.
when I told my Hopkins about it, they bought 3 of them because the price compared to the Stratus, they work really well.
What's the XL? Okay, thanks. Anybody else, or we just go for lunch? Yes, question.
Have you used the library to build like a force sensor?
To build a force-stroke sensor. It has been done with the contactile stuff. I haven't done it with the like we do make. There is a paper where we measure global force and torque, but it's not like what you're thinking about. It's probably the traditional cylinder like ATI cell. But it is doable. I think the challenge again is mating, because an optoforce will have this issue as well, where you've got this elastomer that has to sit between the 2 sides of the sensor and just deciding on how to make those 2 parts together and get to the right stiffness. But the short answer is no, I haven't done it, but I think it's possible. Yeah.
Out of all the methodologies, what do you think is the most viable for covering arms, torso of like a full humanoid? Don't care about the accuracy or like having that high of a resolution, just roughly contact or not, maybe some gains and how much. And it's relatively cheap.
Just want normal force or contact?
Just want normal force, let's say. What would be the most at this moment?
Probably go for something like a resistive, you could go strain gauge, or you have a look at what are they called? Names that flexi force. Yeah, these yeah. Oh, like little flat strips. Like little 3 flat profile strips, and they have a little circle disc in the end. The challenge you have is depending on what you're trying to measure. Like if you're trying to measure hug or something like that, a whole body, then they're very localized. You got to transfer the force on, but you could put something above it, right? So that you'd have a node or something that pushes on it, but then that's connected somewhat rigidly to a plate, or make any sense? Like almost like a pad, but beneath the pad is a little button that presses on the sensor, and you could probably get something out. Depends on your application. I should talk to you more because you can give me some ideas what you're actually trying to do. So. Yeah, question.
Thanks for sharing this advanced technologies in tactile sensing. So my question would be, what do you think of the future of the tactile sensing design? Because it seems like there's no boundary or solutions for all the applications. So do you think the future for tactile sensing design is going to be like multi-modality, like the Picture 360, or they're going to be like different tactile sensors for different applications?
That's a good question. I feel like what's probably going to happen is a guess, but one technology will start to win. Will be shown to be very reliable and completely reconfigurable, and then that will be reconfigured for different applications. Is my guess. There's always going to be special cases where you want extra high spatial resolution. You're going to use a camera, right? But there might be a more general method that works across a wide range of spatial resolutions and force ranges and so on. That would be the technology used. Maybe my guess, but I'm not sure. That's a really hard question, yeah.
You can discuss it.
Yeah,
thank you.
Independent texture recognition.
And I'd say it's a part of the bigger presentation, so it's really a boiled down version of in situ detection, which focuses a little bit introspectively on my work, but if I was to do this presentation just for slip, it would be a much bigger presentation. I would cover a lot of literature and what other people have done. So bear that in mind. So just a reminder, I threw this slide, wouldn't have been in here, but I put it back in as a recap. So this is the behavior that we are hoping to detect. We believe from human studies that this is important, that this incipient slip can give us a lot of information about friction. It seems to be on contact with an object and while we establish the grip, and even before we start to load the object, to lift it, we're getting frictional information from the surface of the object. And this is the mechanical mechanism we think is underlying this, that the finger-spring bridges are opening and folding, closing up, allowing this incipient slip pattern to happen, which normally originates on the periphery and then propagates inwards until the entire contact shears away and starts to slide. And it's true also for rotation. I'll show, I've also inserted a video from the scene before when we get to rotation section. It also happens for rotation slip. The boundary around the edge of the contact area slips first. The reason being that the friction force there is smaller. The finger has a curved surface, and so against the planar object, the forces around the periphery, of course, they must go to zero at some point by the boundary, and they increase towards the center. And so the friction force around the center of the contact is smaller. As soon as it's challenged, it will be the first to slip, and then that, the center of what's left has to take up more of that force, and then it continues to slip. And if we don't respond by increasing the friction force, by gripping tighter, or taking some other preventative action, the object is going to slip. So this is what we're trying to measure. And if we can measure this slip, that's only one step along the way. So there's lots of papers. I'm going to do a very brief hand waving literature review here, but there are a lot of papers that have done slip detection from what we call gross slip. So when the object, the incipient slip process is over, and the object and the skin are sliding past each other, there might be vibration, we might see movement. That's really where the whole field would have started, I think, and there's lots of papers using accelerometers from a long time back to measure that vibration and to detect those slip events. We're trying to do a little bit better, to catch the slip, literally to catch the slip earlier. We're looking at the incipient slip, the onset of slip, not the overt slip that comes afterwards. And if we can detect that incipient slip, that's one thing. We could just respond at that point and say, okay, slip is happening, we should do something. What should we do? There are a lot of papers that just do something. Let's grip a little bit tighter. How much tighter? A Newton? I don't know, 5 newtons? 10 newtons? How many newtons do we need? Well, the answer is in the coefficient of friction. If you can feel the weight of the object and you have the coefficient of friction, all things obeying those simple laws, you should know how much force you should grab the object with. And so having the friction information could be quite useful in modulating our grip force. So the coefficient of friction is the friction force, this tangential force, divided by the normal force at the moment of slip. That's coefficient of static friction. If we can measure it, we can do stuff like this. So here is an early prototype where some slip happens. It's a very simple and early version of the papilla ray, which is now solved by contractile. Some slip happens, a friction estimate is taken, and then from that point forward, we are modulating the grip force in accordance to the tangential force. And what's really interesting, I found it interesting when I first saw it. I wasn't expecting to make the observation, but Ben here lifts the bottle to unload, to reduce the load a little bit, and the gripper relaxes. And then he lets the bottle's weight go back on the gripper, and he pushes down the gripper and grabs tighter. It's a very unusual interplay between the gripper, which is completely stupid in every way, except for it's been told you should modulate your grip force in accordance with the shear force. You end up in this interesting kind of handover where you take the load and it gives the load and you put the force on and it grabs tighter.
Can you show it again?
Yeah.
That's really cool.
So there's a little bit of force we aim for just so we can have some slip. it recognizes the friction, grabs tighter because it can feel the load, and then he interacts with it. So he pushes down, he grabs tighter, he lifts up, it relaxes. My ball, your ball. So that was the very first demo of that, and then I believe I have a slightly more. I'm going to talk about this paper that was in ICRA several years ago. So it's the same demo, just with the version 1 of the contactile dev kit, where again we build some slip. And so we go in with a small amount of force just to get some contact. When we start to lift, it's not enough, slip happens, we measure estimated friction, and then the force control system kicks in and tries to hang on to it. So I thought I'd just talk through this paper. So this was the dev kit version 1, the design which I've talked about before. We're trying to get that fingerprint profile. So in the crudest possible way, we're trying to get a couple of things with this design. We have a profile which is the tallest pillar in the center, then the next tallest north, south, east, west, and then on the corner is the shortest pillars. And that sets up a traction profile or a normal force profile, so that against a flat surface, this will be under the greatest force, and these ones on the corner will be under the least amount of force, which means they have the smallest traction, which means maximum friction force. So they will slip first on the corner and shear. So that's the design. What else to say? Why are there pillars? Well, I talked about the idea of fingerprint bridges, but it's quite hard to build fingerprints and have the nice properties of human fingerprints. So one way to allow incipient slip without independent shearing is just to have independent parts of the skin and have them completely disconnected. So you see a lot of these sensors, and the companies even selling sensors like this, but it doesn't have to be pillar based. You could come up with a loose, we could even make this contiguous, or we could put a really soft elastomer over these so they could be buried in the skin. It's not necessary that they should have a shape, but it's more the mechanical behavior that we're trying to get. So this is just like the simplest way to get there quickly to prove the principle. But I can see an evolution in the skin in the future where it becomes more contiguous, but it still is holding on to those properties literally under the surface of the skin. So anyway, so that's the design. The sensor we mounted on each side of I said modified. This is a gripper from Robotique, and the complaints that Nima was making, we also have these issues where we're trying to now buy a commercial gripper because you don't want to build stuff you like to build stuff and you learn a lot. But if you've got a goal, you want to prove that friction sensing with tactile sensors work, you don't want to waste years of your life building a gripper. So we tried to buy something off the shelf, and we realised that these things don't work very well. Not for real-time force control. So we're trying to do really quick force control. We're trying to send commands, just the force maybe 10 times a second, 100 times a second. The way these work is that you run into a register, and it sees the force that you want. It says, okay, I got it, and then it has its own Ph.D. control system, and then it goes back in the register to see what we want next. And the register is at 8 bits, so it's at 256 force levels, which is not enough. Because it turns out when the object and the interaction is quite rigid, you're really only moving spatially over very small amounts, and you can get big changes in force. So it didn't work for us, so we literally, after fighting with it for a time, we ripped the guts out of it and put a separate motor in. So we used the chassis, the mechanism, the mechanics, but we have our own motor and control system. So disappointing. And I've continuously gone back to the well, searching for the gripper that we want, and I still haven't found it. So how does this algorithm work, this slip detection algorithm? This is our first slip detection algorithm using this sensor, and we thought what we're looking for to detect incipient slip is when, there's different ways to do this, this is one way. We thought the center pillar we expect, we call it the reference pillar, the center pillar which is the tallest, we expect that to be the last to slip. So let's measure the velocities of all the pillars. So imagine, and this is challenging with frame of reference, okay, so imagine you have the sensor which is fixed, and the object which is going to move against it. And between the object and the sensor are these pillars which are flexible. So when the contact is made, as the object starts to move down, all the pillars will go with it. So we should see the velocity in all the pillars will increase at the same rate. They should be at the same velocity. And then things get interesting. The smaller pillars will slip first, so their velocity will drop. In the frame of reference of the center, they literally stop moving. The center pillar keeps bending, so its velocity is still not zero. And eventually, overt slip happens when the center pillar velocity drops to zero. So it's a bending. All the pillars are bending, and eventually they slip, they stop bending. They might even rebound a little bit. You might have a negative velocity for a moment. And so by observing the velocities, you can make decisions about whether incipient slip is happening. So the graph is, I don't know, not my best graph, right? It's not my best graph. It's crazy, but what we're looking at is that you can take the green and the purple as being the left and right sensors. You've got two sensors, so we're trying to show probably too much in this diagram. There are two sensors which are sensing slip, so we have to aggregate that. On the top graph just shows the forces of the sensor. We go in with some normal grip force first, let's say 5 newtons, because we don't know what else to grab, just to make some contact. And then sometime later, the stage will start to lift, and then some slip will happen, and then the friction information is captured, and then the grip force will be modulated down. We grab the object, and so we can lift off, right? Otherwise, the gripper will just slide past the object, and the load force will never go. So it all gets quite interesting in this window here, where there's a little bit of contact, we have some slip happening, we get some information, we grab tight enough to actually lift the object, and away we go. If we zoom in on this bit, yeah, it's there's a lot happening, but what you see is the y-axis is displacement, so the fact that displacement is increasing means the pillars are bending. So they're making contact with the object, there's some bending happening, but they don't just keep going up, they start to flatten off, which means they're slowing down, they're starting to slip, the velocity is dropping. And if we then look at that, so to redshape this and smooth it a little bit, it's quite noisy, look at it in velocity space, this is what you see. So the thick lines here, maybe you can't see so well from the back, there's a thick purple line and a thick green line for the left and right sensors, they're the center pillar velocities. So they're our reference pillars. So we are trying to see when we hope all the pillars go up at the same velocity and when they drop away, there's some proportion. So the rule is slip detection when the velocity of the pillar drops to 60% below the velocity of the reference pillar. So if we trust the software, this is calculating some slip event here and here, here. And so friction estimates are taken at that point. So if you didn't have, and this is an important point, incipient slip detection is not enough to give you friction. You then need to have a ratio of forces. You have to say, okay, I just saw a slip. So we've reached the point where we could take a friction measurement. We need to have two forces to do the ratio. But because the pillar is calibrated to measure force on every pillar in 3 dimensions, you can look at the normal force and the tangential force. And that's under the assumption that the surface of the object is parallel to the plane of the sensor, which may not be true. We haven't tested that, what was the one? You said something yesterday, Catherine? There's always future research or what?
The conclusion to all research is more research is needed.
Exactly, so the conclusion to this research is more research was needed, and that's, maybe we should be testing, and I'll talk about that, limitations when the object is not parallel to the sensor, or it's curved, or it's inclined. But under the assumption that we know the normal direction and the tangential direction to the surface of the object, we can take the ratio of that pillar at that moment and say, this is our current estimated friction. And so it happens, you pop, the pillars pop off, friction estimates are taken, which goes to the controller, which modulates the force. So just briefly, and this is a little bit, it's not a very interesting slide, but just to show you the control architecture, the whole algorithm that we have our, should I look forward a little bit? So we have our two pillar array sensors. It's all very basic prototypes. If we have an Arduino which captures the data, so that gets sent to the PC in real time, and then the PC is the one that runs the control system. It's calibrated, so we don't take in the raw data, we actually take it in and process it, because we've done calibration of the sensor previously, and it might have taken us a few days to do that. and that's that calibration file is loaded in, so the sensor data gets converted to calibrated force values and displacement values. And then we have to make a decision on the target grip force. So this could be a fixed grip, which would be the standard way to do it, or some other simple grip force control, or I'll show you how we make that decision based on friction. And then what you do, this is the control part. You say, well, this is what the sensor is measuring, as there's two normal forces, because we have two sensors. They should be equal and opposite, but they might differ, maybe measurement there and so on. Or if you pick up an object, we're holding it like this, but we could be holding it like that, right? And in the extreme, I could probably, if I'm very good, I could balance this object on my thumb, and then all the weight of the object would be on my lower finger, and the measurement of normal force on the top would be 0. So having the object held sort of vertical changes the way how the control system should work. You measure an error between whichever one of these matters to you, and the error goes to the controller. So it's a Ph.D. controller. It just looks at the error and says, oh, we have an error, we should grip tighter. Or, we're gripping too tight, we should relax a little bit. So two control schemes, one being, this is what we would like to do. So we have detector and signal slip. From that we get a friction estimate, and that gets sent over here. So that's what fills in this grey box. And one paradigm, and the other would be just to have no intelligence, and we just pick a fixed target force, 10 newtons, and that's what we're going to use for everything. And the whole point of the paper was just to show the difference between those two strategies. So, and you can already anticipate what the result is going to be, but I'll show you anyway. So we went through, I'm not going to bore you with all the details of the protocol, but it's sort of lightweight objects, heavy objects, low friction objects, high friction objects, all those permutations, and we do all these experiments and we show that this gripper, it works for all objects and all frictions, whereas a fixed force won't. So this should say, there's a lot happening here. You're watching 4 experiments run in parallel, but just what we see is, was 4 newtons enough? We don't know. Was 6 newtons enough? We don't know. 9 newtons enough. We do the experiment and we realize that, oh no, we just learned it's too heavy, the friction's too low, it's going to slip. It doesn't even grab it, I don't think. This one here is what we call a slow slip. So we have some criteria that we judge slip on, and we say if it's slipped more than a certain amount within a certain number of seconds, we're going to call that a fail, or a soft fail, so a slow slip. Optimal grasp, which is where the control is running, and then we have, enough force. We guessed, well, here maybe you're a little bit too excessive, I'm not gripping too tightly, and we will grip the object.
Can you play it again?
Yeah.
Just so we can.
I might have to go back a slide just to trigger them all. So this one, if it's slow slip, this one should just be creeping out the grasp after it's lifted very slowly. It will eventually come down to the table. And this one is enough, but it's excessive. I mean, we don't need to grip that 9 newtons. I don't know what the force ended up being. So, what was the grip force? And this has a safety margin. We're putting 20% on for safety. So it's about 6 newtons or something. So that's why this one was close to being enough. And then just another example, low friction, high weight. That's the other extreme. And here the forces are, I'm up at the top end now, so we've got, let's start at 9, 14, our dynamic control, and up to 20. And it's the same type of experiment. Like you'll have, this is not enough, this is almost enough, this is money, 20% to spare, and this is excessive. So that's the idea. And the results then, there's a lot here, so let me just point out the main things. These are the parameters of the experiment over here. So cardboard would be one type of friction, another type of friction, lubricated paper, so high friction, low friction, lightweight, heavyweight. So there are the permutations, some information about types of the amount of force that was used by the dynamic controller, not really important. But this table is what matters, and of course, with the And ours is the best. You know, these are all the green marks all the way down for every experiment, so we always grip the object without dropping it with just about the right amount of force. And this will be the table you generate using fixed forces and no a priori information. It's exactly as you would expect. So when you're at the light weight, high friction, here 4 newtons was just about enough, and then so 6 is plenty, 9 is 20 is plenty. And then the other end, it's like this is the very slippery and heavy object. If you didn't know that, you might pick the wrong grip force. You would have to pick 20 newtons to have enough force to grip that. So how do you know? But of course, by measuring friction and contact, you measure the weight of the object through the sensor, and you measure the grip force through the sensor, you always pick the right force. It's a very simple experiment. I mean, this is there's more research to do, right? There's so many parameters we haven't even tried. So the limitation with that is that I made the assumption that the center pillar is the reference pillar. It's the pillar that will slip last. It doesn't have to be the case. And another limitation that may or may not have occurred to you already is that this idea of velocity. Velocity has magnitude and direction. I've just talked about velocity as a scalar. It's not a scalar, it's a vector. So velocity in which direction? And so this works well for a linear motion, but it doesn't necessarily work well for rotation, where the velocity field is circular. And the center pillar never moves for pure rotation. So why should we use the speed of the center pillar as a reference when all the pillars, particularly the pillars on the edges, are moving the fastest? That doesn't make sense. So this is a different paradigm where we don't use reference velocity. The strategy here is that we estimate velocity of every pillar as normal. So that's called the speed, then I should say speed. The speed of the pillar drops below some threshold, which has to be decided just with the noise level. We would say then that the pillar has stopped moving. So remember what's happening. We have an interaction between these pillars on a sensor in the sensor frame and an object. The object is making these pillars move around. And we're trying to figure out has slip happened or not, just by looking at the movement of the pillars. So one way to do that is to say, okay, the pillar is moving, so it must be in contact with the object, and then it stops moving. There's 2 reasons why it could stop moving. One is that the object has stopped moving, in which case for a rigid object, all the pillars will stop simultaneously. But the other reason it stopped moving is because, well, it didn't break contact, it's going to slip back, is because it slipped. So it can't stretch any further and it's kind of sliding past. So that's a different strategy. So if you detect that the pillar has stopped moving, all you can say is it stopped moving, but then there's one more step to decide if it's a slip. You say, what about the other pillars? You look to your neighbours and say, are you guys still moving? If they're still moving, so I must have slipped. I've stopped, so I must have slipped. And then you call that a slip. So it's a different strategy. These are all heuristic, right? So I'll show you stuff later which is machine learning, where you think, well, why is he coming up with these rules, right? There must be let the data talk to itself. So here, back and forward. So just 2 very simple experiments. So we're doing this on a test rig. So we're using the same rig we use for calibration. We do some slip experiments. We have a camera looking from the top, which is our gold standard, which tells us when the slip has happened. So it's tracking the sensor movement. The frame reference sensor and tracking all the pillars. So when we manufacture the pillars, we put tracking dots on. They're actually for calibration, but they can also be used as a reference for the slip detection. And then the hexapod, this steward platform, will move around to generate the relative motion to create the slip. So you can see all sorts of limitations. I'm going to come back to this soon and talk about that. We've got a transparent surface because we want to validate the slip. If you didn't have a transparent surface, it's very hard to know if the slip happened or not. You can't see see what happened. So it's really difficult to validate some of these algorithms if the object has to be transparent. And we've only got one friction here, so we're not going to test any friction in this scenario. And you'll notice in the previous paper, at no point I gave you some algorithm that was velocity based on the reference pillar. We never validated it. It's kind of like the proof of the pudding's in the eating. It's like, let's just come up with an algorithm, hope that it works, put it on the control system, see that it seems to grab the object and go, yes, I think the slip detection is working because the grip controller seems to be doing a good job, but I have no evidence that it does it. So trying to validate these algorithms in incipient slip is really difficult. But bird slip is easy because the object starts moving, so you can track the objects moving in space. But incipient slip is like the object might have hardly moved, or the pillars could bend and no slip could happen, and that movement does not mean any slip. So it's really hard. But having a transparent object is one way to do it. I've had thoughts to build an object with cameras inside, like we do for the human finger, and have the cameras looking out at the surface, but then I didn't change it. So we ended up building an apparatus for we can use them for human studies as the object to validate slip detection algorithms. That's the way to do it. Okay. So that's the test apparatus. I'm just showing you a couple of experiments. We sort of zoomed in on the sensor. Sensor's in contact with this perspex. It's going to move really slowly, actually. And this is a limitation of the work of criticism. We're doing these really slow movements. They're unnatural, actually. And when you lift an object, it's dynamic. It's force that's being applied to the object, not displacement. In this situation, the sensor's moving up in our view, and it's actually into the lab. And then the slip happens, and you should have seen there, and this one's already played. So I'm going to go back one more time. So should move up, it will tell you, so they're all in contact, they've all gone green, which is a good thing about these sensors is that we can feel contact. With camera-based sensors, it might be difficult to know if you've made contact with the surface. You can see shear fields, but knowing that you've made that contact and what the force is might be challenging. We know immediately when the sensor makes contact on every pillar, we know it's in contact. So they move up, and then they pop off and form it. And this one here is moving to the left, so similar. So I was talking to you while this stuff was happening there, so you saw the little animations and slip, and yeah. Oh, it's happening, there we go. Right. And it's a relief when you see it happen in the order roughly that you expect, because like the corners go, and then the next ones go, and then the whole lot. But it's a really artificial movement, it's a fixed velocity. Like what slip happens at fixed velocity, maybe what I call the slow slip, where you just lost the grasp. But like fast slips will should accelerate because it's force driven. So this was Pablo's paper at IEEE sensors, and he got into the student paper found that one didn't inside. But this is so what's nice about this approach, not using the reference pillar, which used to be the velocity of the center, is that we can do rotational slips. So these are rotational slips. And sadly, I'm terrible. I need to do a better job of working with these students because this paper was under review for journal because it's not published because it got rejected and then Pablo graduated and I was like, "You're going to write that paper?" And he's like, "I'm definitely going to write it." And his first week in the job, he emailed me back and said, "Really busy at the moment. I'm not sure I'm going to get that paper finished, so we need to finish this." So we've done it. You know, we've got the data, got the results, but it's not published. But that's how the idea is. So again, the movement's very, very slow. We make contact, they'll go green. It's moving, so they turn red. We know these ones are moving, this one's not moving, it's in the center. Slip. So we know it's slip, it's rotation. The definition of whether that's moving or not is quite tricky because obviously it is moving, it's twisting, but it's not translating. So I consider slip here to be translation. Okay. And you can just, I'm coming up with these crazy rules. Maybe, this is the way the world's gone at the moment. That's data driven. So of course you can put it into using neural networks. There's some of the papers in robotic convolution letters, just using neural networks to interpret the signals and make a decision about brute force. The student here shied away from the brute force control part, partly because the gripper is such a pain to work with, but here he just has like an all or nothing strategy. It's like, oh, slip, like just full grasp, which is not clever, but the stuff is resilient enough to take it. And the other thing is, because he has the rotational slip aspect in, we can actually control for rotation as well. which I'll come back to. And he's Chinese, Chang, so I think that's why he went for without adaptation on the right and with adaptation on the left, because he would like to read from right to left. I don't know, so he has some backwards in my mind. And I thought, but yeah.
I have a question. Just for me to understand, here you're doing sleep detection, not sleep prediction, right?
Detection, yes. I mean, define prediction. It's a prediction.
So this is a very deep question. So there are several papers that claim to be able to basically predict sleep before it happens. They often call it incipient sleep.
Yeah.
And some of this paper, so we've been working on this a little bit with Digit, and I have a methodological issue with almost all of the papers out there that claim to do prediction of sleep into the future.
Yeah, it's an important question, and you reminded me to talk about it because I've had this discussion many times. Yeah, the literature, I think it's converging maybe, but if you go and read it, the terms I feel were not always defined properly or used or misused. So people would say incipient sleep is the moment just what do you mean exactly? I mean, the definition for me is when a part of contact area has slipped. So you've got some contact area, contact between the object and the gripper. If one part, but not all, has slipped, you are in the process of incipient slip is happening. And when all the contact is slipped, then it's overt slip or gross slip. But that incipient slip terminology has been abused. So people would say, oh, it's when the first translation between the object and the gripper happens, that's incipient, the start of slip. But it's a compliant interface, so like you can have just stretching of the interface, or bending of the pillars, with no slip. That's not incipient slip. Or you can have the very beginning of an overt slip where there's some vibration happening and it hasn't quite accelerated yet. That's the beginning of overt or gross slip. So I agree, that the term is abused or misused or not defined well. And it makes it difficult to read the literature because you read papers where they talk about, oh yeah, we detected incipient, or we predicted, or whatever the terminology is. Yeah, I mean prediction, under my definition, prediction will be something else. It would be like, even going as far as, let's say you had, on a previous slip you captured the friction information, and now you can have no more information about what the contact interface is like. And then you're watching the forces, you probably could make a prediction when incipient slip would start. Because you know the force you have and the weight of the object and you learn the friction, so you might have a guess at it. I mean, that would be prediction in my mind, predicting that. If I go any more with the load force, I'm probably going to initiate the incipient slip process. So, I don't know, I'm kind of rambling around the topic there a little bit, but I just feel like it's been confusing, the literature, the way people have written about it. So.
Yeah, I completely agree. And to me, one of the biggest problems I've really seen is that if you want to do detection, even with a data-driven way, it's relatively clear to identify when detection is happening. If you want to predict things before it happens, first of all, you need to have extremely accurate timing and synchronization of the data. We were lucky because we were using time cards, which are these cards that Meta uses on planetary scale to synchronize servers that are like 1 minus 50, 1 minus 15 of a fraction of a second, whatever. But then there is this whole problem of how you also collect data, because it's different if somebody shifts something from you or if you sort of keep the same force and over time the object slowly move. So it's okay.
Yeah, that's a whole new dimension. I mean, how do you control the movement of the object past the sensor? Is it a whole topic in itself? So is it position control, force, constant force control, natural movements like this, where you do loosen the more forces that happens? There's the whole bit around that. And then there's the timing. Actually, maybe you mentioned timing. Something that I No, we've been asked to define the requirements, again, all the requirements of sensors, requirements of algorithms, what are the latency requirements for these algorithms? I think the stuff that we're doing is a little bit slow, probably in the way we implement, because we're chunking windows. We're sort of saying let's take a 200 millisecond window and slide and so on, but like 200 milliseconds is a long time. Like we saw with the human system that we're responding to events within, the whole process happens from mechanical event to force actuation within about 100 milliseconds. In 100 milliseconds, we haven't even finished collecting the data yet. Like, and then we've got to process it, make a decision, send a command. The motor's got to move. It has inertia, so more time is wasted. So then, like half a second later, finally, you make a decision, and the grip force has been increased. Is that too late? Maybe it's okay for some slow-moving applications, but for high-energy stuff like ballistic, so movements and so on, completely insufficient. So there's probably a whole bit on processing that's sort of real time. And the guys at Bristol are working on event-based cameras, so maybe that's an idea where you can process asynchronously as the data arrives at very high rate.
Thank you so much.
Yeah. And I thought I'd just show, so I've been collaborating with the guys at Bristol, and I'm sort of giving my 2 cents and having guys that, all these topics that we're talking about in SLIP, but they're kind of building the hardware and running the experiments. And one such collaboration was to take the tack tip and try to give us fingerprints. So the guys reprinted the sensor like this, and my vision was that I was kind of pushing them, can we do this? Because I think that if we had the ability for the tack tip to have that shear displacement, like something like fingerprints, we could get incipient slip to happen. And so we did. Because previously the designs for the tack tip were very smooth and contiguous, and the material that's built out of this ferro black is, it will bend, but it doesn't like to stretch. So you can't get that shear displacement unless you build in a kind of folded structure. And so we built this one, just to show you what the camera inside looks like. It's tracking the pins. This is the pin displacement you see. And this idea here is already incipient slip, because you get, if everything was moving at the same speed, the displacement of all of these would be identical. They would all go with the object, which is rigid, but they start to slip away on the edge, and the next ring starts to go, and the next ring starts to go, so the displacement sort of diverges. But it again challenges the sensors. You can't see the contact surface. We don't know which of those rings is in contact. So we kind of cheated a little bit here by saying, look, we know it's this ring and the next one and that one, but the one after that is not in contact for this normal force. So let's just ignore those at all. So that's a problem with these sensors. You can't see the contact area. So this is a bit lazy, but there's a video here. I'm not going to play it with the sound, but I'll just let it run. I'll sort of chatter over it. So yeah, this has been published if you want to go and read. And what's nice about some of the experiments done in here is that they're natural experiments where they have the object held and they load it on a rail of gantry, so when the weight of the object gets too big, it would slip and actually fall under gravity, which is a nice improvement on just testing on the rig. There is a machine learning approach used to detect slip, which is a bit black box, but the data do it. It seems to work. There is another version of this coming, so working with Ben, his idea then was to take this tip and to use a neuromorphic camera with it, and so that work is happening. And George, you're involved in that, are you? No, okay. I thought you might have been that one, but that's so he's got the neuromorphic camera behind the skin, but even then he still wasn't happy with there's something a bit too rigid about those rings. I know they look like fingerprints, but they just are too bound to each other. Even the ring itself is too stiff around its circumference, so it's a laxity, and so then he's gone for a design which ended up being a full circle, and it now looks like a pillar, so he's got a bunch of pillars on top of the tack tip to do incipient slip. So that paper is coming soon. It's just been submitted for review. Anyway, so the reason to show the tack tip was to give a shout out to the boys in Bristol, but also just to say that the idea of incipient slip from these, if you design the skin well, you could do it on any sensor. You could do it on the digit, you could do it on the outside probably. it's more about the design and mechanics of that. Okay, so we better wrap up now. So remember, I put this slide in just to remind you that torsion is important. So some of the early experiments we did, the first videos I showed you when we were, for ICRO, we were centering the object in the gripper to lift it. We ended up having to put marks on the table, marks on the object, and to get down and to line them up perfectly well before the gripper went to work, because if we didn't, if we were off by even a millimeter, you'd end up with this torsion due to gravity, it's this torque. The object would tip over the gripper, and then that would actually cause slip more easily than the weight of the object. So it turns out, yeah, like for an object that's not that heavy, you try to hold it on its end, you try and hold it right at its end, you end up needing quite a lot of grip. This object's not heavy, but if I have to hold it by its end as well, torque, I've got to grip really hard. So, and that's probably more likely to cause a slip than it is the weight of the object. So controlling for torque is probably a bigger issue than controlling for weight. And just to say also that gravity and torque from gravity are probably some of the biggest forces on the object. To try to get the forces that you get from gravity, you have to accelerate or decelerate at quite high rates to generate those forces. So like moving the object around the world is not such a big issue. Colliding with objects and just countering its own weight and torque are important. So this is a quick one, also not published. But you can do this stuff if you have a step detection algorithm that's correcting for friction, and you also build the friction aspects into the controller, and based on your knowledge of the geometry of the sensor, you can also control for torque, friction-based control of torque. So you know the friction, you measure the torque, the force, the weight, everything. You can modulate the grip force, not just to the weight of the object, but also to the torque on the object. So the gripper, when we off-center the center mass, it will increase the grip force in response to that. So there's also the and we had a little chat about grippers, and I had a moment about it there also, but yeah, this was another gripper I bought when I got to Dublin, so I'm going to try again. There must be a gripper out there, and we talked to the robotics distributors, and they said, we think we have the gripper for you. This is a mono-robot RG2. That's a dog, it just doesn't work. So we ended up ripping the hook out and put a stepper motor in. So if you know the gripper that I need to do grip force control, you let me know, because I'd rather not have to build these things. And the challenge with doing this is that we have really fine position control, so we can do great force control. So once we have contact with the object and it's rigid, we make really small movements with the stepper motor and it's geared up and we get good force control. But then because it's so heavily geared, if we want to open it, it goes, it's like right, it goes like this for 2, 3, 4, 5 seconds just to open it up. So it's like, how do you get the fast movement of the gripper? And I don't know. I'm not a gripper person. So, last one, this is the last thing. Just thought I'd throw it in because we're in the algorithm section. It wasn't just about a SIPI and SIP. This was just demonstrating some of the other utilities of having a select zero array. And you might think that the spatial resolution is poor, so you would never be able to get fine textures from it. But through sliding and exploration, which is a large part of how humans explore texture, because I think there's evidence. We were talking about Stephen's paper yesterday. I think there's some stuff like this in that paper about scanning and if you were to make contact with a fine texture. I know the gel site can do it, right? Because it's amazing. The digit or whatever is a high resolution vision camera, but humans can't do it as far as I know. You cannot touch a really fine grained texture straight down and know the texture. You have to slide and explore. And that information could come through vibration, but don't forget also there is a spatial array of sensors in your skin. And as you move, parts of the object move to different, they slide across and there's information shared as an asperity on this material moves across lots of mechanoreceptors. There's a temporal pattern of movement. And so you can sort of correlate across channels to figure out what the texture is, even though spatially you might not have the resolution that you need. So here we've printed a bunch of textures that are relatively fine grained, and then we slide the sensors. The spacing between the pillars here is 8 millimeters, and some of the textures are down to like, what's that, 0.5 of a mil. So they're much smaller than the spatial resolution of the sensor, and you just slide it across. And I suppose the punchline here is that with one sensing unit, just using vibration, if you knew the speed, I think you'd do okay. It's easy, like you know the speed of the movement, and you just see pop, 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 and you figure out what the spatial frequency is. But imagine you didn't know the speed. Then what would the spatial frequency be? So with no speed information and a single sensor vibration, you can't do it. It's impossible. But if you had two or more, then you start to be able to do it. The way to do it without being agnostic to speed is to use the phase. So what I mean by phase is that these signals should happen in or out of phase with each other, depending on the spacing between the sensor pillars and the spacing between the texture ridges. So what will happen is one is going on, pop, 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 pop. The other one will join the trains in and pop, 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 pop. They'll be out of phase with each other. And so by looking at the relative phase between signals on different pillars, here is just for example, this is pillar 3 and 7. 3 is in top right corner, 7 in the bottom right hand corner here. The sensor sliding across the material like this. These are the signals we would see. I think it's just the Z displacement. So for texture J, which is the big one, it's like they're almost 180 degrees out of phase. And then for some other signal, they're a bit smaller in Z deformation because the features are a bit smaller, but here they're almost in phase with each other. So it all depends on the relative size of the spacing. So just to show that it is possible to discriminate these very regular textures like this with a sensor that has spatial resolution is really poor, just by exploration, just slide across, and you can do it without needing to know the speed. What it would look like in natural textures, I think phase is a bit going to be a bit rudimentary. It's probably going to be more like a cross correlation between those channels to look at the information content. As one sensor travels over along the line, the other one follows behind it. You should be able to see it, the same pattern coming just delayed in time behind it.
Do you ever compare pillars that have different heights? And don't you see, because you're comparing like two that have the same height, and I would expect that also matters.
Yeah, I think some of them are different heights, even just by looking at geometry.
Not the texture at pillars. You're looking at a pair of pillars that have the same height, so I kind of expect them to feel the same thing, but a taller pillar or shorter pillar, there's another aspect of the
Well, I
difference.
guess these are, I'm not sure, I need to go, I'm sorry, but I need to go back and check for this paper because we had different versions of the skin here where some were like sort of optimized for incipient slip and they had the different pillar heights, and some, I think she had them as
oh, so they're flat, okay.
They might be flat, and I'm not sure which is for this paper. But it's a good point because with the different heights then you're probably getting even more information about like this one's under more force and this one's less. So anyway, I just wanted to show that to you. And there we are. So the whole idea of this incipient slip is that creating traction differentials somehow and allowing shear force displacement however you manage it, by pillars or rings or fingerprints or whatever, or just really stretchy skin encourages incipient slip. If you can also measure the forces at the time of slip, you could take an estimate of friction under some assumptions that you know the normal and the tangential directions, and that could be used as part of your force control strategy. And just to comment on that, sorry, I feel like am I okay for time? I'm nearly finished now.
Take us one or two more.
I'm starting to get into a point there, so I think I'm not book time too much. This difference between incipient slip detection and friction estimation, there's a subtlety in it that's really important, which is how it informs your response strategy. Because if it's incipient slip, you're like, okay, something's happening, and it's great that I'm getting an early warning sign because the slip has begun. You still don't know what to do. It's like, I think I should grip tighter, so I just grip tighter. But how much more tightly should you grip? I don't know. And then you're in this sort of like search, it's sort of like a gradient descent that has to be done really quickly to stop the slip from happening. Whereas if you have the friction and you're feeling the weight of the object, more or less you know exactly what to do. Straight away, it's like you got the friction, you know the weight, just go to that force, that's your target, get there quickly. So it changes your response strategy in such an important way. And I should say, to go back, the thing is, do humans do that? I don't know. I don't think we're like loading, we have a friction variable in our head and it just gets loaded at 0.57 is the friction. And I think we're probably much more error driven than that, so maybe we are using the incipient slip, stop the slip strategy, which is like a gradient descent reactive thing. But if you had the friction and you were storing that information, even implicitly, it would change your control strategy. I said it's difficult to validate slip in realistic scenarios, and we also had a discussion there about how that turns up in the literature, which is just a dog's breakfast of like poor definitions of what is slip and how slip is validated, what do they actually mean when they say validated. Half the time more, they never actually looked at the contact interface to prove that it was incipient slip. It was probably overt slip, probably neither. We don't know because that's often not validated. And it's really hard to do because you can't see the contact interface. And these were my closing remarks from yesterday, but I already made them. So yeah, we're going at a rate of knots. Things are getting better in the sensor space. It's nice to see some commercial offerings at decreasing price. So as it's economy of scale and stuff. So as those companies do better and sell more sensors, the price just will drop. And the challenge is overall, we talked a lot about durability. So we probably will start to see academic papers with durability testing as one of the requirements, but it will be nice to see that in there. You'll say my sensor is wonderful, it has all these measurement properties, but it's also tough as hell and it will last for a million cycles. Calibration, drift, compensation are challenging. And we even see in commercial companies, they charge you more money to do this. It's difficult. In the old days, nobody cared. You got a sensor, you got a signal out of the sensor, that was good enough. Now the expectation is to resolve into force and displacement. But maybe you don't care about that if you do machine driven. Requirements, we don't know. So this is the challenge. We don't know what the killer application is. So we're kind of fumbling around trying to figure out what do we need. One sensor for one application might not be good for another. And then market readiness, I talked a bit about that. The challenge from a market readiness point of view is like if you, there might be another point on this below, maybe I should just go forward. Yeah. So integration with commercial grippers. So I'm trying to get you to put yourself in the shoes of an entrepreneur. So let's say you develop a tactile sensor technology during your Ph.D. and you want to commercialize it. You'll go through this whole process inside the university and file my patents. You got to fight with the university and convince them to invest. It gets expensive, so you got to convince them to spend money on it. And in the meantime, they'll say, you better find a customer for this soon because we're not going to pay for this patent to go to a regional national phase, which gets really expensive. Hundreds of thousands of dollars and euros. So you start talking to people in the industry and say, I've got a great technology, do you want to use it? And there's different places you go to insert yourself into the supply chain in a way. So you could say, look, my business model is, we just integrate with normal grippers. So you just stick them on, it's easy. But there are no grippers that you can integrate with. So what do you mean integrate? In what way? Okay, mechanically you can take the fingers off a gripper and screw them on, and now they're integrated. Well, not really, because your sensor signal goes over here. The gripper has a closed commercial control system over here, and they don't talk to each other. So then you're trying to convince the gripper company, could you put my sensor into your gripper and make it part of the API, and we'll build a control system, and then they're kind of like, they might say yeah, mostly they'll say. So it's kind of hard to get into the market if you're a sensor company, you want to sell to a gripper company, and they're like, not doing that yet. And they don't see the market yet either. And force control. So even to prove to the gripper company that it can be done, if we had force control gripping, we could show them the demos, and then, but they don't sell force control grippers. They do. Probably the best that you can find in the market is force target. So you set a force target and it's a stop. So let's say it goes to 10 newtons as a target. It goes to 10 newtons and it locks and stops. You want to change it, you read the register and moves. It's just slow. It's for safety. You're trying to handle parts. You don't want to crush them, so you set a force limit, and that's about as good as it gets at the moment. It's sad. So the other way to come at this is, what's called a full stack solution. So you say, which is really brave to do this, and some robotics companies come with this approach. Some of it's driven by venture capital investment, where they say we want all of the pie, we don't want to be a piece of the pie. Because if you're selling to a bricker company, you're a very small, you're a component supplier, twice removed probably from the customer. So you're getting a tiny amount of the money that's coming out of that. Isn't it better if you go full stack, so that you become like a sanctuary or whatever, and you sell everything? You say we'll buy the robots in, we'll make our own grippers, we make the sensors, we do the vision. You know, Nima's going to join my company. We're going to do the intelligence, full stack. We're going to need a lot of money, so you go to California and they give you 700 million or something like that. So those kind of companies need huge investment, incredible risk, very ambitious, but like that's going too much. And so this is the challenge that we have. Where do we insert ourselves in this ecosystem? Am I a sensors company, a gripper company, component supplier, full stack? And that was kind of a wrap up for not just today, but all the stuff from the previous part of the presentation about sensors and so on. Okay, so I think impact, huge impact, probably in the shorter to medium term in all of these areas that you're aware of. Logistics, probably not so much prosthetics. I know it's really cool, everybody always thinks of prosthetics. The market's tiny, so you're going to make no money here. There's all sorts of issues with agency, autonomy, and that users don't really want this stuff necessarily, so just be careful with prosthetics. Logistics is mega at the moment. With Amazon, for example, they're trying to solve these problems. Emergency response, smallish market. Manufacturing is huge, very difficult, very regulated and constrained, and really high requirements. Manual handling, probably in the distant future. That's, we have an issue with an aging population. We don't have enough people to care for older people. We don't have enough money to pay for older people to be cared for. So technology would be a useful addition. Robotic surgery, we heard a lot of from Catherine yesterday. Telepresence, work from home for also manual labour. And agriculture is a huge one. So the margins in agriculture are absolutely tiny. The work is brutal. Like there's some really sad stories of workers being abused. They're brought in low-wage labour to pick fruit in Europe, in the US, all around the world. So there is a motivation to try to bring technology to solve that issue. But that leads to the last point. There is huge societal disruption coming from this technology. So this is going to become a political issue as well. When all these jobs are taken, what are we going to do at that time? What are people need to do? And that's probably not our. Do we have a responsibility? You should think about it, but I'm not going to solve it. Okay, thanks to all the guys in the team, a bunch of collaborators, Heather and Ben, who went off to found Tactile. You see them on LinkedIn. The guys from UCD, most of them have graduated now. The guys from Australia, Cash is now Bristol, we were at one. Guys from Belgium, who did all the stuff with Sophie on the tour. And his two of the boys from. You need to get your face up here, George, is that alright? Someday from Bristol to Nathan and we had some previous members of that. Okay, thanks for your time.